Hello. Have you wondered how computer viruses work behind the scene? Much of the material we'll cover is well known in the binary forensics community, but they're often not easily accessible to beginners. Let me be very clear. This course is not trying to teach people how to destroy computer systems, because everybody can already do so more effectively by dropping a hammer on their laptops. I want to share knowledge about an unconventional type of software engineering. After finishing this course, you will walk away with a different perspective of how software runs. If you are a computer science student, I hope you will gain the ability to research further on this topic with all the tools we provide. If you are a software engineer or administrator, I hope you can design your system in a way that is less likely to be taken advantage of by viruses. Here is the outline of this course. We'll begin by getting familiarized with the Linux executable format and tools that are useful throughout. Then, we'll discuss constraints of writing a computer virus and things that you never think about but are crucial to making them work. You'll see why it's surprisingly hard to write a virus. Following this, we'll talk about virus infection algorithms that enable them to spread with detailed code walkthroughs. Then, we'll see an open source Linux virus framework that I created, which lets you experiment and craft your own self-propagating code. Of course, we'll study example viruses and see how much damage they can do if you're infected by one of them. Finally, this course will be concluded with a discussion related to ethics and hacking. I hope you find the content engaging, and I will see you soon. Hello and welcome. This course is about Linux virus engineering, but the things you learn here is transferable to other operating systems, such as Windows. Contrary to common conception, the use of Linux is everywhere and on the rise. It was first started in 1991 as an open source project and is gaining popularity ever since. The Linux kernel source code can be viewed and modified by anyone. As soon as new hardware comes out, companies like Intel will write code and submit to Linux kernel to support their products. People rely on the stability, performance, and security of Linux as it becomes the main backbone for data centers. If you use Android, you rely on Linux every day. If you drive a Tesla, the infotainment system runs on some flavor of Linux. Just about anything you do online, shopping, posting images, the backend server will likely run Linux. It is everywhere. Some people argue that Linux is immune to malware. Obviously, it's not true, otherwise, this course will not exist. For those who are not convinced, I want to share with you some real stories of computer viruses in the early days. The Morris worm. A worm is a form of computer virus that propagates through a network and is capable of infecting a large number of computers. Here is what FBI says about this worm. A maliciously clever program was unleashed on the internet. It sounds like a compliment here because it was written by a college student from Cornell in 1988. The program took advantage of different vulnerabilities of other programs running on the Unix operating system and spread to other computers on the network. Due to the fact that the same computer may be infected more than once, many computers were slowed to a crawl as they repeatedly get infected or infecting other computers. Even though the worm doesn't explicitly do any damage, such as deleting files or stealing secrets, it effectively managed to shut down the internet as machines are just busy infecting other machines. To quote his own words, he was trying to merely highlight the weakness present in many networks at the time. But the cost to remove and restore infected machines was between $100,000 and $10 million at that time. Another example is the ramen worm that targeted Red Hat Linux distribution. All it does is to change the default entry file for web servers to a page that contains a picture of ramen. Imagine when you type google.com or amazon.com, you get a static page that talks about ramen. So the takeaway is Linux is written by humans. Humans make mistakes. Therefore, Linux is not perfect. Given enough resources and time, a virus for Linux can be engineered. A possible reason for this misconception, and people rarely see news for a Linux virus, is that the user base is too small, and that makes them less of a valuable target than those using Windows. But what people rarely notice is that Linux dominates over 90% of the cloud computing market, Internet of Things, as well as half of the global web servers. Imagine a modern version of the ramen virus spreads again and defaces half of the websites on the internet. What would the world become? Whether you have worked with Linux or not, I hope you are convinced enough to invest your time into this course. But I want to mention again, the unconventional software engineering techniques that power computer viruses are applicable to other operating systems. At the end of the day, virus creators need to exploit flaws, patterns in software design, or human nature, and that holds for all operating systems. I want to show you a live demo by writing a small piece of virus and see it silently infect other binaries in the same directory without changing their original intended functions. And then, we will send our infectious program to a website called VirusTotal. It is able to run various commercially available antivirus engines, telling us if it's malicious or not. Hello and welcome back. I hope you enjoyed the demo and are excited to embark on this journey. I want to first go over some tips and advices before we go full speed. It's strongly recommended that anyone researching malware should use containerized environment to avoid damaging your computers. It is standard for many security companies to maintain air-gapped labs, not only at network or software level, but also physically to search people going in and out to make sure they don't unintentionally bring in USB sticks that can leak virus samples to the outside world. Our Hello World virus probably doesn't sound that scary, but I still want you to be aware of proper hygiene in case you go down this path further. We will be working inside of Docker containers for the rest of this course. The Linux virus framework that was used in the demo has just everything you need. You will see a setup video later in which we will build two images, one for ARM Linux and one for x86 Linux. One of the best things about this framework is that it allows you to write a virus once and compile for both platforms, so you can research the behavior easier in a cross-platform manner. It's also worth noting that if you run a container that has a different chip than what your host machine has, you will encounter some reduced performance. Having both containers allows you to choose the one that works best for you. So, what exactly is this virus framework I've been talking about? It's an open source project that I started, which aims to solve many challenges for those who want to research Linux malware. You might have seen various tutorials or articles online about novel techniques used by a virus, but it's very likely that only small parts of the code is published, and reproducing it could be difficult. It's possible that the author doesn't specify the compiler commands or the complete environment for people to build it. Imagine you see something that could be interesting, but it's targeting 32-bit Linux, which nobody uses outside of embedded world. You would have to port it to 64-bit in order to study it. This framework implements popular infections and redirection algorithms that work out of the box for both ARM and x86. You don't need to start from scratch, as you can borrow various components to build something new. What this framework ensures is that the build environment is hermetic. It doesn't matter what Python or C compiler you have on your system, because the dependency is all taken care of for you. Any work you do is guaranteed to be reproducible by other people. If it works on your machine, it's going to work on your mom's machine, and even your cat's machine if it has one. In the upcoming videos, I'll demonstrate how to set up the framework and the development environment so you can read the source code and experiment with pre-installed tools that will just work out of the box. Hello! I want to show you a demo in this video. Here is the plan. We will build a simple self-propagating virus that prints Hello World using the virus software framework that comes with this course. We'll look at different parts of the framework as we learn various infection techniques down the road. The framework makes researching virus so much easier because it has bundled up all the building blocks for you. By the end of this course, you will be able to reproduce this demo completely on your own. After our toy virus that prints Hello World is compiled, we will infect an arbitrary binary on our system. Let's infect the pwd program that prints the current working directory. Then, we will run the infected executable and see it silently infect other executables in the same directory. By analogy, after the patient 0 was first infected with the virus, it will organically spread to other patients in the vicinity. I have prepared the virus for you already, and let's take a quick look at the code. We will introduce the virus framework and the files in the repository later in the course and show you how to set things up. The file we're looking at is called self-propagating virus. It contains a main function, and the structure looks pretty much like a normal program. We first define a string literal hello world, and then perform a write system call that prints the string onto the screen. Then, we invoke this function that replicates all the code here in this main function and infects executables we can find in the current directory, including child directories 2 levels deep. It basically means that our virus will print hello world and then search for other executables. As soon as another executable is infected, it will do the same thing, print hello world, and infect others. I'm going to run some commands to build this virus and an infector program that allows us to infect our patient 0. If this looks alien to you, don't worry about it. I will explain what these commands are later in the course. First, let's compile the virus, and then let's infect our pwd program. After this command is run, we have made a copy of the original pwd program into the temp directory and infected it with our toy virus. This infected copy is named as victim. Let's see if it still works. The victim binary first prints out hello world, which means our virus has been executed. Then it prints out the current working directory, and this is what it's supposed to do. We have successfully infected a copy of the pwd program without changing its original intended function. Let's copy over some other common programs on the system and see how the virus from patient 0 spreads silently. Let's copy the ls CPU program that prints out CPU information. Then, let's run our patient 0 that is highly infectious. Let's run our copy of the ls CPU program again. It now prints hello world before printing CPU information. Our patient 0 carrying the toy virus has silently infected another binary in the same directory. This is pretty cool, but I want to show you something even better. Our virus framework that comes with this course has tools that allow us to experiment different infection algorithms on a large amount of executables. Instead of providing a specific executable to infect, we can pass a directory to it, telling it to infect all binaries inside of it. Again, I'm skipping a lot of details about the algorithms we use here, since we'll discuss them later in the course. What you see here is a giant table of infection results. The first column is the name of the executable, the second column is the type, and the last column is the infection result. The infection rate is pretty high, as we only failed for 12 out of 570 binaries. We will cover many different infection algorithms, and each of them comes with different trade-offs that might give you different results here. Let's see what VirusTotal says about our infectious patient 0. It looks like none of the available antivirus engine marks it as malicious. If you write something like this for Windows that attaches arbitrary code to executables, which recursively tampers with other executables, I'm sure many will complain loudly. Linux antivirus is such an underinvested market, but it's a very legit target. I know this demo just makes everything look so easy. It is not, even for seasoned software engineers. We will cover all the pieces that are crucial to the inner workings of a virus and reveal a software engineering process that is somewhat unconventional. By the end of this course, you will have in-depth knowledge on how a virus is built, as well as the ability to craft your own self-propagating code. I hope this gets you motivated, and I will see you later. Hello and welcome back. I have borrowed my wife's brand new MacBook to show you how to set up the development environment from scratch for this course. Please don't tell her I'm installing a virus framework, otherwise I'll be sleeping on the couch tonight. The first thing you do is to open your terminal and pull down the repo. Because Git is not available out of box, we'll need to install it. While that's downloading, let's go to browser and download the Docker desktop. We need to use it to interact with containers. Make sure you download the right architecture for your Mac. If you're on older models before 2020, you're likely using an Intel chip. If you see anything here that starts with an M, it's Apple Silicon. Dinosaur Macs using PowerPC chips are no longer welcomed here, unfortunately. After it's downloaded, drag and drop Docker to the application folder. It looks like the Apple developer tools are installed, and we can use git command now. Let's go to the repository for the virus framework, copy and clone the repo to your home directory. What we are going to do is to start Docker for the first time. You can just use the recommended settings. If you see a prompt to install Rosetta, please do so. It can speed up emulation on Apple Silicon, and that comes in handy when you want to experiment code on x86 containers. Now, let's go to the virus repo and read the development process section. We have already cloned the repo and are ready to build some images. Copy these commands and run them. One of the features of our virus repo is to allow us to write code once and compile for both platforms. This command builds images for both ARM and x86 and starts running development containers. If you look at Docker Desktop, indeed, we have two containers set up. You should see one with warning because it has a non-native CPU architecture. We will encounter reduced performance because it requires instruction translation or emulation. But it's useful for one-off experiments to ensure the virus works on different platforms. After that's done, let's connect to them. Because I'm on ARM natively, let me use the ARM container. The prompt has shown that we have successfully connected to the container, and also there are some weird boxes due to missing font. It shouldn't affect anything and you can install them later. Let's go to the propagation section of the README and perform a virus infection. Copy these commands and run them. We'll talk about what they do in detail later in the course. This command builds the test virus as well as the infector tool we'll be using. Now, let's infect the ls program with our test virus. The infector tool internally ran the infected binary with dash dash help option, and that's why we're seeing the usage text here. But right before that, it also printed running virus code, which means our injected virus also ran. Let's see if we can infect all binaries in the user bin directory. Pretty cool. We just reproduced the demo you saw earlier, and your development environment is fully set up for this course. Hello and welcome. In this video, I'll show you how to set up the development environment for this course on a Windows machine. Let's open your favorite shell. For this video, I'm using the PowerShell. You can install it using the instructions linked for this video. Let's enable Windows Subsystem for Linux and install the Ubuntu distribution. Now we can run Ubuntu in Windows. Next, we will need Docker to interact with development containers, so whatever we do happens inside a controlled environment. Select Download for Windows. After you install it, you should see a Docker icon on desktop. When you open it, let's go to Settings and ensure we enable the WSL2 engine so we get better performance. Go to Resources tab and enable integration with the Ubuntu distribution we just installed. This enables us to interact with Docker from inside Ubuntu. Click on Apply and Restart. The next step is to clone the virus framework repo, which contains all the materials for this course. Copy and clone to your home directory inside Ubuntu. Because we're running Linux inside Windows, we will also need to change the Docker socket permission in order to interact with Docker services. Some might argue that the permission here is too loose. They're not wrong, but for the sake of this course, let's just ignore that. Now, you should be able to build the development containers following the instructions in the virus repo. Let's go to the development process section and then copy the commands. This line builds a Docker image for both x86 and ARM, and then starts running the development containers. One of the features of our virus repo is to allow us to write code once and compile for both platforms. After that's done, let's connect to them. I'm running Windows on x86, so I'll be using the x86 container. If you're running Windows on ARM, you should pick the ARM container for better performance. It would work if you pick the other one, but just slower since your computer needs to translate instructions to perform emulation. We're now inside the x86 container, and it's also conveniently shown on the prompt. Whatever we do here would happen inside the container. If things go wrong, we'll just remove it and start over. Now, let's reproduce the demo you saw earlier. If you go to the propagation section of the virus repo, you can copy these commands to build the code. We'll explain what these are in detail later in the course, because we just want to test if our development environment is set up correctly. This command builds both the test virus and the infector tool we'll be using. After everything builds, we can copy and run the injection command to infected binary. In this case, I'm infecting the ls program with our test virus. It looks like the infection is successful. Internally, the infector tool runs the infected program with -- help option, and that's why it's printing the usage here. But before that, it also printed running virus code, which means the injected virus also ran. Let's try to infect all the files inside the user bin directory. It looks like we're able to achieve a pretty high infection rate, and we have reproduced the demo we saw earlier. Your environment is now fully set up for this course. Hello and welcome back. I'm using a freshly installed Ubuntu 2004 to show you how to set up the development environment from scratch for this course. The setup should be similar for other flavor of Linux distribution as long as it has Docker support. The first thing you do is to open your terminal and pull down the repo. Because Git is not available out of box, we will need to install it. After that's done, we can clone the virus repo to the home directory, which contains all the code for this course. Then, let's go back to the browser and download the Docker desktop. We will need it to interact with containers. Make sure you click on the official Docker website. In the Install Docker Desktop section, there are two steps. The first one is to set up Docker's package repository. Let's click on that and run all the commands in this box one by one. If you have used Linux before, it's basically setting up a repository for a Docker installer to download stuff from. The second step is to download the installer and use this command to install. Make sure you specify the correct full path to the downloaded file. Alright, looks like the install is successful, and let's launch Docker. It needs to be running in the background to provide service to interact with Docker containers. Let's go to the repository for the virus framework README page, and let's check out the development process section. Copy these commands and run them. This command builds images for both ARM and x86 and starts running development containers. If you look at Docker Desktop, indeed, we have two containers set up. You should see one with a warning because it has a non-native CPU architecture. We will encounter reduced performance because it requires instruction translation and emulation. But it's useful for one-off experiments to ensure your virus works on a different platform. After that's done, let's connect to them. Because I'm on x86 natively, let me use the x86 container. The prompt has shown that we have successfully connected to the container, and also there are some weird boxes due to missing font. It shouldn't affect anything, and you can install them later. Let's go to the propagation section of the README and perform a virus infection just to make sure our environment is set up correctly. Copy these commands and run them. We'll talk about what they do in detail later in the course. This command builds the test virus as well as the infector tool we will be using. Now let's infect the ls program with our test virus. The infector tool internally ran the infected binary with -- help option, and that's why we're seeing the usage text here. But right before that, it also printed running virus code, which means our injected virus also ran. Let's see if we can infect all binaries in the user bin directory. Cool. We just reproduced the demo you saw earlier, and your development environment is fully set up for this course. Hello and welcome back. We will start this chapter about executable format, and I want to warn you that this is arguably the most boring chapter of this entire course. For those who listen to music, you probably have heard of MP3 file format, but I bet my money that you probably don't know what MP3 stands for. Do you know the internal file structure of MP3 files? It's likely that you don't, because as long as it works, who cares about the format? This is the same thing for the executable format on Linux. A lot of smart people came together and agreed on a format that captures important information on how to load a file into memory and how to execute it as code. I just want to give them some respect for the amount of effort they put in. There are groups of hackers somewhere on this planet who study the format and figure out flaws in it so they can find opportunities to infect the file with a virus, all without breaking the original executable. If we ever want to understand how they did it, we will need to get familiarized with the file format first. You don't need a PhD to understand this format, and we don't really need to be an expert in it right away either. You will be one though, as long as you accumulate the knowledge bit by bit. I believe the best way to learn a format is by inspecting the file. For this entire chapter on executable file format, we will see all kinds of tools that will be useful throughout. This chapter really sets the foundation for the rest of this course. It will pay dividends when we get to the chapter on infection algorithms. So sit tight, and I will see you in the next video. Hello! In this video, I will give you a high-level overview of the structure of an executable on Linux. It's fine if you cannot understand every detail because we will explain things more in subsequent videos. The picture you see here demonstrates the internal structure of a typical executable file on Linux. This file format is called Executable Linkable Format, or ELF. The white boxes on the left are different parts of the file. It first starts with the header that describes the metadata of the executable, such as the CPU architecture that it was compiled for. Then, we have a program header table that describes the runtime behavior where different parts of the file are loaded into memory. Following it, we have a series of white boxes, and each box is what we call a section. You probably have heard of these terminologies before. The text section contains code that we wrote. The RO data section contains read-only data, such as string constants. At the end of the file, we have a section table that contains detailed information of these sections. The arrows you see here depict different parts of the file, encoding relevant information for other parts of the file, and they're all connected logically. This might sound a bit abstract, and that's why I want to introduce a tool called OBJDump. It can help us visualize different parts of an executable. You can get this tool by installing the bin-utils package, and it should be already available from within our development container after you have followed the setup videos previously. Let's try this tool on an arbitrary binary with -D and -J option. The -D option shows the instruction in human-readable format, while the -J option limits the decoding of instructions to a specific section. Let's take a look at the text section first. The text section contains machine instructions for code that we wrote, and it's generated by a compiler when you program in some high-level language such as C++. The instructions are displayed in ARM assembly because I'm currently running Linux on ARM. The first column on the left shows you the file offset where this instruction can be found. The second column shows the raw instructions in hexadecimal, and right next to it, a decoded assembly form. This information is very useful when you want to mutate certain instructions and double-check if you have done it right. Keep this command in your stash as it will come up very often. The text section of an executable will be loaded into memory assigned with executable permission because ultimately we would want to run the code. Now let's take a look at the RO data section, which contains read-only values. For example, whenever you use a string literal, it will show up in this section and you can view it directly on the rightmost column. Perhaps the takeaway is never ever hardcode your password or API secrets inside your program as string literals, because the first thing reverse engineers do is to dump all the strings when they try to hack your program. The RO data section of the file will be loaded into memory with read-only permission. So if a virus tries to modify contents in RO data section, it will crash the program with a segmentation fault, and that's why we need to be careful not to violate access permission. There are some smart ways to mutate permission for RO data section, but that's pretty suspicious as nobody expects read-only data to be writable. Let's move on to the data section. This is where initialized variables or global variables live. For example, if you have a global variable and initialize it with some value, the initial value will be stored in the data section. Although in this picture there's nothing really useful, it might be different when you run this tool on other binaries. I just want to reiterate visually in terms of a program. You can kind of follow the arrows from parts of the C program to where things are in an executable file. Global variables go into data section, the constring literals go into RO data, and your compiled code go to text section. So far, we have been looking at the files sitting on your hard drive. It will look very different when they are loaded into memory for execution. But how does operating system know which part of the file to load and assign what permission? In the next video, we'll start talking about details of the executable format and what made running an executable possible. Hello, let's talk about the executable linkable format. Before we dive deeper, I just want to say that the format specification is pretty long and you do not need to memorize them for this course. We will talk about important pieces that make your life easier down the road, but you can always consult the Linux man page for additional details. We have seen this picture on the right, and today we'll use the readelf tool from the bin-utils package to explore different fields of the file header. It's already installed for you in the dev container. Let's run the tool on any binary with the -h option. The -h option tells the tool to decode the elf header in a human-readable way. Each elf executable has an array of magic numbers that always start with 7F, 45, 4C, and 46. You can verify this with the XXD hexdump tool. It turns out that the first number, 7F, is a bit arbitrary, but the subsequent three numbers are ELF in ASCII. According to our specification, the magic array also tells us the architecture of the binary, among other metadata, but it also reserved 7 bytes at the end of the array for future use according to this paragraph at the bottom. It's a very common way in software engineering that you reserve some space for future use because you're not sure what you would need down the road. Having extra space makes your software more future-proof and is a signal of good design. There's a downside to this approach though. Depending on how strict this is enforced, you shouldn't be surprised that people will start abusing it. Although 7 bytes is not a lot of space, people put all kinds of stuff in there, such as names of the virus or organizations. Here's a normal binary on the top, and a modified binary with extra data inside the magic array padding. Writing extra information here doesn't break anything because our kernel actually completely skips processing these bytes, and we haven't seen this change for years. More importantly, this gives virus creators a simple way to test if a binary has already been infected by it. For instance, after a virus has taken over a host binary, it will stamp the magic array in the elf header with some unique signature. A virus can then use that signature to prevent infecting the same file again. This idea might sound simple, but it's very effective. Avoiding to infect a binary multiple times helps a virus to reduce unnecessary activities and the chance of being caught modifying files. You can also append bytes at the end of the file, but this approach is superior because it doesn't change the file size at all. Therefore, it requires less code to perform file operations, and that gets translated to a virus with smaller code size. But the downside is, this raises some red flags and people can easily see it by dumping the header. Antivirus software might use this as a heuristic to say that this file might be tampered with and should be closely monitored. Like I said, even though we haven't seen changes to ELF format in years, this doesn't mean it won't change in the future, but I still think this trade-off is well worth it. A small virus is crucial to its survival and success of propagation. The next thing I want you to look at is the entry point address. This points to the first instruction we'll execute once a program is loaded into memory. You can think of this as a pointer to a function that it will be the first function we run. This field basically tells our operating system to execute code starting at this address. You might have guessed, what happens if we fake an address here and have it point to arbitrary code? Absolutely, this is what people do. We have an entire chapter dedicated to talking about how to redirect program flow to run a virus later in the course. Let's look at two other fields, the startup program headers and section headers, pointing to other smaller header structures. They describe how things are laid out in the file and in memory. These offsets are like links that connect to other smaller structures inside the file. The rest of the fields below it record how big the headers are and the number of smaller header entries that could be useful if you want to iterate through each of them. To summarize, we have looked at the ELF header, which contains a whole bunch of metadata about a program so our operating system can load it into memory and run it. We also introduced a simple technique that allows a virus to quickly test if a binary is already infected by checking the padding bytes at the end of magic array. In the next video, we'll dive deeper into program headers and section headers. We'll see what they do and how people abuse them. Hello and welcome to this lab, where we practice skills we learned in the previous video. If you haven't watched the setup video, I highly recommend you to do so because a lot of things we do will happen inside a Docker container where all the dependencies are already installed for you and things will just work out of box. The first thing you do is to make sure that the Docker desktop is running in the background, which provides the services that allows us to interact with Docker containers. Now let's go to the virus framework repo, which you already cloned in the setup video. There are two commands to run depending on your architecture. If your host machine runs on ARM chip, you should use this arch64 command to connect to the ARM container. But if your host machine uses an Intel or x86 chip, you should use this command to connect to an x86 container. Selecting the right architecture makes things run faster because your host machine doesn't need to do extra work to perform emulation or virtualization. Because I'm on an M1 Mac, I'm going to connect to this ARM container. As you can see, the prompt here conveniently displays the architecture so that you will not get confused as to where things are happening. Whatever we do today will happen inside this container, and if things go wrong, we can easily blow away this container and restart everything. For this lab, we're going to navigate to the temp folder and do some hand modification on an ELF header. Let me remind you of a technique that was mentioned in the last video. Some viruses will mutate the ELF header to stamp them so that they can avoid infecting the same file over and over again. We can check an arbitrary ELF and then display the header by running this readelf command. In this case, let's display the ls command. You can see that this is the original magic array for this binary that comes pre-installed in the Docker container. And indeed, the magic array starts with 7f, 45, 4c, and 46. You can use the hex dump command xxd to also dump this file in binary format. And because this file is quite big, let's only dump a handful of bytes first. You can see that the first 4 bytes are ELF, which is in ASCII, and you can see this directly from the dump. What we're going to try today is to stamp those bytes that are reserved in the magic array for future use according to our specification, and then stamp them into something arbitrary and to see if it still works. We can do this using the vim command. For those who haven't used vim before, it's basically an editor that allows you to edit a file either in text format or binary format. But before we do, I want you to make a copy of the ls binary into the temp directory. And let's call this copy ls copy. And you can see that this command has been copied over, and it should work exactly the same way as our original ls command. And you can run this copy command to ensure that it works as intended. You might have noticed that whenever you run this ls copy command, it doesn't print things out nicely with those color. It's because the original ls command is actually an alias. You can achieve the same thing by passing a command line option to tell it to display everything in color. Now let's modify this ls copy program and then stamp the elf header with our custom message. Whenever you open some file with vim, because this is binary, you can see these bytes, raw bytes, cannot be rendered in a human readable way. What you can do is type in column %, exclamation mark, xxd, and hit enter. What this command does is it will convert the entire file into hex dump. As you can see, it shows the raw bytes as well as the corresponding ASCII form. Now, let me remind you that according to our specification, the first 16 bytes are the magic array, where the last 7 bytes are reserved for future use, and all the programs should just ignore them. Now let's see what happens if we fill in the last 7 bytes. We can try something arbitrary. Let's see, 31, 32, 33. If you haven't used Vim before, you can enter editing mode by pressing I once. As you can see in the left bottom corner, you're currently in insert mode, where you can just modify this bytes however you want. And once we're done editing, you can press the escape key once to exit out of insert mode. Because we already converted this file into hex dump format, what we need to do is to revert the change back to the binary format. You can do so by typing this command on the bottom left. And the first part is exactly the same as what we used before to convert the entire file into binary format, but with the -R option, it essentially reverses the operation. And then we have this file in binary format again. Because we're editing this file, we need to actually save all the change that was made. You can do so by typing column W and Q. And W means we want to write all the changes into the original file, and Q means after that we exit. Okay, now we have successfully edited this ls copy program, and let's dump its header to see what's going on. This is the header content for our modified ls copy program. Now, I want you to dump the original header for the ls program so we can compare them. The top half is the modified version, the bottom half is the original version. You might have noticed the difference to the magic array. The last couple bytes have changed to 31, 32, and 33 compared to all zeros in the original ls binary. Let's see if this modified binary still runs. it still runs and then prints out all the contents in the current directory. Let's check out some other commands like help. It looks like this binary just works without problem, even though the header has been mutated. And now you have successfully stamped this binary with some arbitrary information in the header. For those who are curious, the ELF header format can be found in the ELF man page. You can simply search for the ELF man page. And let's see where it describes our magic array. In the ELF header section, it describes a structure that was used to encode various information for the ELF header. And it turns out that the magic array that we're referring to is the very first field that is named as eIdent, which I think it's another way of saying identity array. This array has 16 bytes, and the last couple bytes were reserved for future use. You can read more by scrolling down to the eIPad section, and it says programs which read them should ignore them, and this is what we are taking advantage of. Modifying the padding here does not change program behavior. What if we modify other fields? For example, let's change the magic number here and see what happens. Let's change the last character of ELF into something else. Instead of 46, let's change to 47. And make sure you reverse it back to the binary format, commit the change. And let's run this modified binary. Now the operating system is telling us that it's encountered some executable format error. This is expected because the specification language is pretty strong, as it says these fields must be encoded into a certain magic value. Otherwise, it's not a valid ELF. And in this case, the operating system refuses to load the modified binary here. So what exactly is giving us this executable format error? We should check the kernel source tree because there's got to be a line of code somewhere that performs this check and rejects this binary. And maybe if we read the code there, we will see some other checks that are performed on the ELF headers. Here is the Linux kernel source tree, and let's go to the bin format ELF file that contains the kernel source for loading the binary. And the function of interest is called load ELF binary. And let's see where it's defined. Here we are. This is the main function that defines various tasks that the kernel performs before the binary is loaded. It looks like there's a default return value here, and it's defined as executable format error, which is exactly what you see when we ran the invalid ELF binary that we modified. And let's see where the check is happening. From this comment, it seems like our kernel is doing some simple consistency checks on the ELF header before the binary is loaded. And it is comparing the eIdent field, which is the magic array, against some constant value, which is ELF, as we see here. And we can pretty much conclude that our modified binary failed this check, and then the kernel gives us an invalid executable format error. Let's continue and see what other checks the kernel is doing. From this line, the kernel is checking if our ELF binary is an executable or a dynamic library. We'll talk about these flags later in the course. And then it checks the architecture to ensure that the binary is actually compiled for the target platform. For example, For ARM Linux, we can only run ARM binary. For x86 Linux, we can only run binaries compiled for x86. And then we load some ELF program headers. And then for each program header, we perform certain operations to do some sanity checks. This function is pretty long, but feel free to read the rest of the source code. At the very end of the function, the binary should start to run successfully. Let me summarize what we did in this video. We modified an arbitrary ELF binary and then stamped the ELF header to contain some custom messages by taking advantage of the fact that a couple bytes at the end of the magic array is unused. And the modification itself does not change the program behavior at all. And this technique is used widely by viruses to inject unique signatures into binaries so that they can skip infecting the same binary over and over again. By looking at the kernel source code, we've located the function that performs the ELF header consistency check before a binary can be loaded and run. I hope you get a feeling of how people find ways to exploit certain things by reading the standards as well as the kernel source code. People don't usually manually mutate the ELF header, and later on we'll see a way to do this programmatically. I'll stop the video here, but I suggest you to continue exploring, modifying other parts of the ELF header and to see what happens. Maybe you will find some brand new ways to exploit the standard. Welcome back. Previously, we looked at the ELF header structure and introduced some techniques to avoid redundant infection. In this video, we'll take a deeper look at the program headers step by step. The ELF header has two fields encoding the file offsets where you can find these smaller header structures. Let's use the readelf tool to dump the program headers that contain crucial information of where the operating system should load parts of the file into memory. The -L option prints all program headers, while the W option ensures that the output format looks best on a wide screen. The output might look overwhelming. Let's look at them one by one, following the arrow marker on the screen. And let's focus on the important stuff first, and you will learn the rest as we progress throughout this course. For those who are interested, the ELF man page contains a longer version that describes each field in detail. Each row of the table you see here describes a specific chunk of the executable file and where they are supposed to be in memory. The first row here is describing a block of bytes starting at offset 0x40 from the beginning of the file, and they should be loaded into memory at a relative address 0x40. We can see the starting file offset from the offset column and the memory address from the virtual address column. We load in total 0x1f8 bytes, and they also occupy the same size in memory based on the file size and mem size columns. The first entry is marked as read-only, denoted by the flag R from the flag column. If we were to visualize this on the left, this entry essentially tells the OS to grab those bytes from disk and copy them over to our process image in memory. The first row is of type PHDR, which is reserved for a program header table. When this table is loaded into memory, our kernel can further decode and access other entries in the table, so we can understand where information or code is stored. The next entry in the table tells the OS to load the location string of the program interpreter into memory with read-only permission. The program interpreter's job is to resolve dynamically linked libraries if your program links to external libraries. For example, if you use printf in your program, it comes from a C library. We're loading the interpreter path into the memory so that whenever we need to use it later, we can find it. If you are not familiar with dynamic versus static linking, we'll talk about them very soon in other videos. Basically, if a program is dynamically linked to external libraries, we'll need some help from the program interpreter to load them before we can invoke function calls. The next entry is perhaps more interesting. This is a segment with executable permission, denoted by capital letter E from the flag column. A segment is basically another way of saying a block of bytes loaded into memory. And you can guess that this segment contains our executable code. What's a little weird is that bytes from file offset 0 all the way to some offsets are mapped, which kind of overwrites what we mapped for the previous two segments. This is what Linker does by default for my Ubuntu Linux on ARM, which might look different than what you see on your end. Even though this behavior is completely valid, we're probably assigning executable permission to a segment larger than what we actually need. The entire thing from offset 0 all the way to 0xC3908 are executable. This is an important fact, which later will become clear that some infection algorithms will analyze the program headers and piggyback onto executable segments to inject a virus. We'll come back to this in the chapter that talks about infection algorithm. The next entry is also loaded into memory, but with read and write permission. This is where we keep the global variables and other things. For those who are actually doing the math, you might find that when you add a virtual address and the memory size of the last segment, it doesn't equal to the starting address of this segment. Hopefully you can see the red text up here between two segments. Why is there a gap between the last segment in memory and the current one? This is due to the fact that these two segments have different access permissions, and we can only control permissions on memory page boundaries. In other words, the executable permission for the previous segment will also apply to the gap between these two segments, if it just happens that the size of the contents in the previous segment is not exactly a multiple of page size. For visualization on the left, the yellow boxes are what's actually used, but the red boxes of permission assignment is a little bit bigger. The gap constitutes another opportunity for virus to thrive, and we will introduce an algorithm that inserts a virus into this gap later in the course. The fundamental idea that people are taking advantage of is the granularity of how operating systems assign permission to different segments. I want to talk about one more segment before we move on. As you can learn the rest of the entries from the ELF man page, let's take a look at the note segment. This is mapped to memory with read-only access, since it mainly contains metadata about the program, such as a hash that uniquely identifies the file. Like the type suggests, it's just a note. This segment is unused under most circumstances and is nonetheless mapped into memory. This gives malware designer a chance to sneak in malicious code and mutate the permission flag to allow execution. This is a very blatant way of injecting a virus, as nobody should expect this segment to be executable. However, many antivirus software actually don't check for this pattern, which in my opinion is a big red flag to identify suspicious programs. And this is one of the infection algorithms we'll go over later in the course. The high-level idea of program header is it's a simple mechanism to tell the operating system to load chunks of bytes from disk to memory and set up appropriate access permission. We will save the section to segment mapping table that you see on the bottom to the next video. It will be best explained after we introduce the concept of sections. Welcome back. Last time, we looked at the program headers that tell the operating system how to load executable files into memory prior to execution. In this video, we will look at section headers, which describe different parts of the file on disk. If you remember the last video, there was the section to segment mapping table at the end when we dumped the program headers. The mapping suggests each segment defined by a program header consists of one or multiple sections. The yellow boxes are different segments from the last video, with an access permission assigned according to the red boxes. The blue boxes on the left are chunks of bytes loaded from the executable on disk. On the right, they can be redrawn in a slightly different way according to the section to segment mappings. The smaller pink boxes of sections are composed into segments. Our visualization from the last slide might be a little inaccurate because there could be more than two sections mapped into a single segment. Here is how we interpret this mapping. The first column contains the index of the program header entry that defines a segment. Each row tells you what sections are combined into a segment. If you follow the white arrow, this entry says, for the first segment defined by the first program header, there is no section inside. Indeed, the first entry was created for the program header itself. The yellow arrow says the second segment contains the interpreter section that loads the name of the interpreter into memory. The blue arrow is for the executable segment. It has a long list that contains many sections, including the text section for the code we write, as well as init for constructors. The green arrow points at a read and write segment, which contains our data and BSS sections that you're familiar with. The mapping table is generated based on the file offset range defined for each section and program header. In other words, as long as the file start offset and the size of a section falls within the segment's range, it will be included in the corresponding segment mapping. Let's take a look at the section header table. You can use the -s option to print section headers. They look surprisingly similar to program headers. For each section, we know the file offset, the memory address offset where the section is mapped into memory, and the permission flags. I want to highlight these executable sections, which contain letter X in the flags column. The uppercase letter A means a section occupies some space in memory and they must be loaded by our operating system. On the contrary, if you look at the last section, which is for section string table, it doesn't have any flags. What this section contains is an array of names for all sections. The name of this section has no runtime effect and therefore, the operating system doesn't need to load them into memory at all. Because we know the string table offset, as well as the read-only data section offset highlighted by the yellow boxes, let's dump the contents and see what's there. The XXD hex dump tool has a -s option for dumping bytes from a certain offset of a file. We'll use the section header offsets from the previous slide. On the top, we are able to directly see the ASCII string names for all sections in plain text. On the bottom, we see what looks like format strings inside the RO data section. If you use an editor and change some of the strings in RO data, you will observe updates immediately next time you run the program. File offsets really come in handy when we want to find out the contents of a section and modify them to our liking. When we put program and section headers together and spot check them, they're consistent in file offsets and execution permission. The red boxes on the left is a set of executable code sections which are put inside of executable segment on the right, and the range of the segment encompasses the range for these sections. The yellow boxes on the left is a set of note sections which are put inside of note segment on the right. Later, when we talk about infection algorithms, you'll have more chance to juggle between these tables and ensure that they're consistent. Why do we have so many different types of headers? This is a common question for many people. They're all different abstractions of information at different layers. You can think of the ELF header as the top-level abstraction where you get some general metadata about the CPU architecture, but without knowing the internal details of what consists of this executable. The program header describes the runtime behavior on how operating systems map chunks of the file into memory with different access permissions. The section headers capture the organization of different parts of the file stored on disk, which is more of a static description. All these tables are generated by the compilation process and the information must be consistent across the board before an executable can run. We will take a look at the binary loading process in the next video, and hopefully you can connect all the dots together. Hello and welcome back. In the previous videos, we talked about program and section headers and explained that there are different layers of abstractions. In this video, we'll walk through the entire ELF loading process to give you a clearer picture of what's happening when we run a binary. Back in the days when I graduated from college, this is one of the questions big tech companies asked if you want to work for their Linux team, such as Facebook, VMware, or Oracle. I want to pause here and ask you, how would you answer this question on what happens when you execute a binary on Linux? Typically, this is an open-ended question, and the point is not really to test you on the loading process per se, but to test your knowledge on various operating systems fundamentals. We will unwrap this and expand to relevant knowledge you should be aware of as we go. But keep in mind that this video is meant to be a high-level introduction rather than digging into various parts of how things are implemented in the Linux kernel. We will focus on the design trade-offs and how viruses take advantage of them. The kernel would first examine the ELF header to perform some sanity checks as we saw in the previous videos. It checks for the magic values in the header to ensure it's indeed an executable, and the compiled architecture must match our machine. An ARM CPU cannot understand x86 instructions natively. If you attempt to run a binary that is compiled for a different architecture, it will not work without tricks like emulation. It then checks the type of the ELF binary and only allows executable and shared objects to be loaded. We have seen ELF header has a executable type field that encodes this information. The shared object is a special executable that is position independent. Let me give you an example of what this means. When you write code on the right to modify a global variable inside a function, your compiler will generate assembly instructions, which translates to loading variable I from the current address of this line of the code, plus a fixed offset. Even though this variable I lives in memory and has a concrete address, the instruction doesn't use a hard-coded value for it. Instead, it encodes a relative offset from the current load instruction. If the current load instruction lives at 0xAA00 and the variable I lives at 0xAA16, the compiler will encode the difference, which is 0x16 in the instruction. Regardless of where this load instruction is run, we will always use the offset to locate the variable I. This is what we call position-independent code. Position independence is very important because it allows libraries to be inserted into programs. This is the mechanism we use when a program calls some external libraries such as printf. The code for printf is loaded from disk and shared across different programs that use it. A single copy of the code is mapped multiple times into different address spaces. The picture on the right depicts two different program address space layouts. Because the library that provides printf is position independent, they can be executed regardless of where they live in memory. I guess this is why we call this type of executable shared object, because they're intended to be shared and loaded at different addresses. This is also true if you run multiple instances of the same binary. Now this picture shows the address layouts for two instances of the same program. Even though the segment size are exactly the same, the layout looks different. Things are shifted around due to a kernel defense mechanism called Address Space Layout Randomization, or ASLR. This is done by the kernel to make memory bugs harder to exploit, such as buffer overflow, because mapping segments differently every time a binary runs makes guessing addresses for important information harder. I will not demonstrate this attack as I have linked resources for you to read offline. For modern compilers, it's the default to generate position-independent code as it facilitates address space layout randomization. How do you know if something is compiled as position-independent executable? It's displayed as the part of the ELF header. And in our Ubuntu dev Docker container, most programs are compiled as position-independent code, but I found a couple tools in GNU Build Essential package to be the exception. This mechanism affects viruses in subtle ways. If you think about it, a virus is kind of like an external library that we inject into a normal binary. Therefore, virus creators must ensure that their malicious code is compiled as position-independent code so that it works regardless where it's injected. This mechanism can be turned off by system administrators, and the kernel checks the configuration prior to creating segments. You can read through the kernel source of the bin format elf file if you're interested. We'll continue talking about loading process in the next video. Hello! Let's continue where we left off last time. You probably wondered what this is when we first saw it in the program header. Our elf loading process will use a string that is stored in the interpreter section, which points to a program that can be invoked and perform shared library loading for us. This binary is called program interpreter, or in some places, dynamic linker. We will use these names interchangeably. Locating shared libraries and resolving symbols require a bit more knowledge into the ELF format than the kernel has, so people created a separate binary to perform the job. The kernel only needs to know what it needs to know. However, this opens up an attack vector. Since the dynamic linker is just a normal binary on your system, people have exploited this by supplying a modified version of the dynamic linker that silently loads malicious functions. For instance, when you try to use printf, a modified version of the dynamic linker would map a malicious version of the printf function into memory instead of the one you expected. This is called dynamic linker hijacking. Programs that require external libraries are considered as dynamically linked. You can avoid this attack entirely by statically linking your programs so they're completely self-contained without requiring an extra loading step. While this sounds ideal, why do people not always use static linking? If you remember the picture from the previous slides, a single copy of the library tends to be shared by different programs. When everything is statically linked, we would have one copy of the library per program inside the ELF files. This results in huge waste in disk space, as it translates to hundreds of copies of very commonly used libraries. If you want to link your program with a newer version of the library, say a more efficient version of the printf function, you would need to rebuild, redeploy to all programs that use this library. With dynamic linking, you only need to upgrade once, as it's shared across the entire system. I hope you can see the trade-off and why people are taking advantage of this. For virus writers, they typically compile code as position-independent executable, as I explained earlier. What they also ensure is the virus must be self-contained and not dynamically linked to any external libraries, such as printf. Basically, it's very challenging to locate functions from external libraries loaded dynamically inside a virus in order to call them. This makes writing virus very hard, and later we will see some ways to alleviate this using the virus framework you set up. After the dynamic linker finishes loading external libraries into memory, the process address space is fully set up and we're ready to invoke the first instruction. In the next video, we'll put everything together and walk you through the loading process. Welcome back. We talked about trade-offs for dynamic and static linking previously, and also introduced a defense mechanism called address space layout randomization. Let's piece everything together and walk through the binary loading process. We will be referencing bits and pieces from the bin format ELF file in the kernel source. I recommend you to read through it when you get a chance. The operating system will first read the ELF header from disk and perform sanity checks to ensure we are looking at a valid executable. It will scan the magic values, target architecture, and executable type. If anything doesn't look right, we will get an executable format error. Based on the starting offset of the program headers, the kernel looks at that location and starts to inspect the program headers one by one. For each program header, it loads the specified range of bytes into segments and put them at an address based on the values from the virtual address column. For each segment, proper access permissions are also assigned according to the flag column. If the binary is compiled as position-independent executable, the kernel calculates randomized offsets that can be used to shift segments in memory. This logic will be skipped if the executable is not position-independent, as the load segments will always live at a fixed address. Remember, we always randomize heap and the stack, unless it's turned off explicitly. If a program is dynamically linked to use external libraries, the kernel runs a program interpreter or dynamic linker based on a file path from the interpreter section highlighted in the red box above. The dynamic linker loads requested libraries into address space and resolves symbols, so our program can call functions from the loaded libraries. After the segment setup is finished, we will start executing the first instruction in our executable, which corresponds to the entry address field in the ELF header. And this is it. I hope now you can put everything together and obtain a mental model of what happens before a binary runs. You should be able to explain to other people how to answer this question in a more in-depth way. It's okay if you want to treat the loading process as a black box, as long as you understand why we must compile our viruses as position-independent code, and they must be completely self-contained without dynamic linking. In the next video, we'll take a look at what happens after you hit the ELF entry point. Hello and welcome! We've talked about how the kernel loads a binary into memory, but the whole process feels a bit abstract. In this video, we will explore ways to inspect the loaded binary visually via the procfs. The procfs, or the proc file system, is a special file system on Linux that presents information about processes and other system information in a hierarchical file-like structure. It's basically a way that the kernel exposes extra information about our system. You can see what's offered by listing all files in the /proc directory. There exist some subdirectories with numerical names, which represent running processes identified by their process IDs. For example, when you run a program, the operating system will assign a unique number to the program in order to identify it. In the picture above, it looks like on my system, I have 3 processes running, highlighted by the red box. Inside these directories, there is a file called maps that can tell us what the process address space looks like in memory. Let's build a simple program and check out its address space. First, let's ensure the Docker desktop is up and running because we'll need it to interact with our development containers. If you have rebooted your machine, you will need to start your container as well. I would recommend you to watch the setup videos if you haven't. Let's navigate to the virus framework repo and connect to a development container. I'm using the AArch64 ARM container because it matches my host machine architecture. You should use the x86 one if you're on an Intel chip. This bazel build command compiles a target, specified after the double slashes. The target we're going to build is in the infector folder called victim PIE. Let me remind you, the PIE means position independent executable. Let's also build a non-PIE version of this binary. The compiled outputs are in the temp bin directory, and let's just copy them into the temp folder to save some typing. Let's run the PIE version of the binary and put an ampersand at the end so it runs in the background while we inspect its address space. The number you see here is the PID of the program we just ran. You can use this number to navigate the procfs. Let's use the cat command to dump the maps file. The file we're looking for is called maps under this PID folder. Now we see a big table that describes the address space for the victim program. The first column is the memory address range for a segment. The second column is the access permission, with R being readable, W being writable, and X being executable. The third column is the file offsets, where these bytes were loaded from the ELF file. On the far right, it also displays the file name. We have 4 segments loaded from our victim binary, and these correspond to 4 load entries from the program headers. We also have a heap and a stack segments, as well as other libc libraries. It looks like they're loaded because the victim binary invoked a print function that comes from libc. I'm not sure why libp threads are loaded. My guess would be there are some implicit dependencies and they have to be pulled in. If you remember this file, it's our program interpreter which helps us load these external libraries. It has an executable segment, as well as read-only segment and read-write segment. We loaded the program interpreter basically as a whole. Let's quickly cross-reference the program headers. Indeed, we have 4 load segments that correspond to the 4 entries we saw in the address space above. Let's run another instance of the same victim PIE binary and observe if there is any difference in the address space. While the first instance is still running in the background, the second instance is assigned a different PID. Here is what its address space looks like. If you only look at the rightmost column, these 2 instances are the same because we're running the same code. But if you look at the heap and the stack segments, they start at slightly different addresses. This is kernel's memory randomization at work to make certain memory bugs hard to exploit, and reverse engineers, hackers, will have a hard time cracking your program compared to having everything with a fixed address. The first 4 segments from our victim binary, as well as loaded external libraries, also have shuffled a little due to address layout randomization. You might wonder how these addresses are calculated. Let's walk through some examples using the program headers. The kernel first obtains a random starting point to construct the address space. Because the first segment's virtual address offset is 0, it will construct the first segment right at this random address starting point. When you add the mem size to the start of the segment, you will compute the end of the segment. Remember, access control can only change at the page boundary, and that's why the end of the segment is slightly larger than what you have computed. The number will be rounded up to the next page boundary. The second segment's starting address is determined by adding this number from the virtual address column to the random address space starting point picked by the kernel. And that's how you get this number. It will be slightly smaller than what you have computed because, again, we have to start the segment at page boundary. Likewise, the end of the segment is computed by adding the mem size to the starting address of this segment. The kernel repeats this process for all loadable segments. I hope you can conclude that the virtual address column specifies the relative offsets from the random address space starting point that the kernel picked in order to facilitate randomizing segment addresses. This is true only for PIE binaries. Let's run a non-PIE version of our victim binary. If you look at the last column, we have the same contents as the PIE binary, but the starting addresses for the first 4 loadable segments have very different starting addresses. It's almost many orders of magnitude smaller. Where do these numbers come from? Let's dump the program headers for the non-PIE victim binary. You can probably tell these segment addresses come directly from the virtual address column. For non-PIEs, this column encodes the absolute address where each segment would start from. What about address randomization? Let's find out by running the second instance of the non-PIE victim. As you can see, the first 4 loadable segments from our non-PIE victim binary have the exact same starting address. There's no shifting involved for them, and that's why hackers can find a fixed address to exploit memory bugs and expect it to work reliably because these segments will always be loaded at the same address. If you look at the stack and heap segments, as well as the loaded external libraries, they, however, have different addresses than the previous instance. So address randomization works only on parts of the address space for non-PIEs. I want to provide a quick recap of what we just saw. For programs that are compiled as position-independent executables, which are also known as shared object file according to the ELF header, the kernel loads segments based on offsets in the program headers by adding them to a randomized process image starting address. This basically means they will be different every time you run the same program. Since instructions are position independent, it doesn't matter how we shift the segments as long as the offset is fixed. For programs that are not position independent and are shown as executable file type in the ELF header, the kernel always loads segments to a fixed address, even across invocations, due to the fact that instructions in text segment might reference data using a fixed address scheme. We cannot shift the segments, otherwise we will not be able to locate variables correctly. For example, those in RO data or data sections. For heap, stack, or dynamically loaded libraries, they always have randomized locations. Infecting PIEs and non-PIEs involves different techniques, as you will see later. It's much easier to infect non-PIEs for some algorithms, since loadable segments have fixed addresses. That's why I always suggest you compile your program as PIEs. In fact, recent versions of GCC compiles PIE by default, which is a good thing. But you might still see some non-PIEs floating around on your system for whatever reasons. By the way, the address numbers you see here might be a little different than what you see on your system, but the principle is the same. I hope you now have a deeper understanding of what the process image looks like in memory and how the ELF program headers can affect it. Welcome back. Previously, we looked at the ELF loading process prior to running a program. In this video, I want to talk about the program entry point and answer this question. What is the instruction that is pointed to by the entry point? 3 options are listed above. Let's pause here and take an educated guess. Option A says, we will run the main function right after a binary is loaded. This might sound straightforward, but it's not true. If you notice the parameter arg_count and arg_value passed to the main function, it feels like some work must be done to prepare the parameters before main can run. Option B says, the entry is pointing to some code in kernel. This is also wrong, because why would we jump back to the kernel right after it sets up all the segments? How does the program know the kernel address to jump to? This leaves us with option C. It turns out that all C programs by default are linked to a special C library called CRT0, which is also known as the C runtime, that sets up the environment prior to running the main function. Whenever you compile a program, it is linked automatically for you. The most popular standard C library is the GNU libc, which provides code for many common functions that make your life easier, such as printf. You might see other versions that are specialized in generating smaller code. For example, the micro C libc that's popular for embedded systems where space is a constraint. Let's look at glibc for now, and you can see the source for the startup code in assembly here, targeting x86. You don't need to be an expert in assembly, as the comments are pretty good. The _start is the canonical entry point label, and the entry point field in the elf header encodes the address of the instruction at this label. The program flow looks like the diagram on the right. Upon executing a binary, we will find the first instruction pointed to by the elf entry point field and then run the startup code there before running the main function. The startup code performs low-level setup, such as preparing argc and argv. These arguments were left on stack by the kernel, so we will need to load them into registers and pass them all the way to main. It also calls libc start main function that performs constructor calls. When you have a global variable initialized to some deterministic value, it will be constructed here. If you have worked with C++ before, you know it's strongly discouraged to use global static variables because the initialization order is not deterministic. When one global object's constructor calls another global object's member function, we don't know if the other object is constructed or not. This is also known as the static initialization order fiasco. Long story short, somebody's gotta construct these global static variables, and it happens right here before main is called. You shouldn't be surprised that the destruction for global static variables will happen after main is finished. In some applications, you might want to register callbacks to run after main via the add_exit function, and the callbacks happen here as well, that are usually for user-defined cleanup purposes. The reason why we talk about libc startup code is to give you some idea of what's happening behind the scene. I want to introduce something that a virus can take advantage of. The libc is linked to virtually all programs you can see because everybody requires the startup code to perform setup. In other words, we can safely assume that most programs contain a similar set of instructions prior to running main. If we can find a way to hack the startup code, we will be able to affect almost all programs. Later in the course, I will share with you a method that I devised in 2023, which hijacks program execution flow inside the startup code to run a virus. After the virus has finished running, it will continue the normal program flow from where it was left off. We have come to an end for this chapter on the ELF format. I hope you are not too bored, because in the next couple chapters, you will be able to see practical applications of the knowledge you'll learn here in virus engineering. I will see you in the next video. Hello and welcome back. Congratulations on making this far. I believe you now have a solid foundation to grasp the core concepts of this course. In the upcoming videos, we will examine code snippets and learn the specific techniques needed to create a computer virus which differ from regular software development. First, I want to walk you through the steps and considerations crucial for building a virus. A virus is essentially normal code that runs on your CPU. Here is a typical build process for normal software. You write code in a high-level language like C++. The compiler generates assembler files with a .s extension, which looks like something shown at the bottom left. You can also code directly in assembly when needed. Some people write highly optimized code for viruses to gain precise control over specific functions, and we will cover some of that later in the course. These assembler files are further compiled into object files, which are binary files containing raw CPU instructions. When you inspect these files, you will see a series of numbers that CPUs can directly interpret. Next, these object files are linked together into a single binary. The linker combines everything and resolves addresses, allowing functions from one object file to be usable by code in another. As discussed in the previous video, what happens before main runs? The C runtime CRT0 is linked by default at this stage. ELF sections are also formed based on a linker script that describes the layout of the executable file. Although most people don't think about this unless working with embedded systems, our linker provides a default linker script that works for most cases. After this process, we'll have a ready-to-run executable. However, the process changes slightly when writing a virus. Virus code cannot dynamically link to external libraries because it lacks the ability to find them at runtime. Therefore, our virus must be fully self-contained or statically linked. Since a virus typically runs before the host it infects, we don't want to execute the C runtime startup code twice. We need to provide our own startup and cleanup code, such as copying and restoring registers to their original states before running the infected host. We want to make it appear as if nothing has happened. We will tell the linker to use our own version of the startup file and disable the default one with --no startup files. Additionally, we need to provide a customized linker file to purposefully arrange sections in the desired order. Typically, we tell the linker to place all executable code of the virus in consecutive blocks, allowing it to be extracted as a whole binary blob. This extracted virus code can then be injected into other binaries. In essence, building virus code is a variation of building normal software with certain restrictions and customized building blocks. Don't worry about it if it's the first time you see behind-the-scenes actions for compiling software and it might sound overwhelming. We will examine these steps one by one in the following videos. Hello! Last time we talked about high-level workflow of building a virus, from writing code to extracting the virus as a binary blob that can be used to infect other executables. In this video, we'll discuss detailed challenges involving writing virus code and how we can work around them. First, because the virus will be injected into other binaries, we have no control over the exact location where a virus will live inside a host binary. This effectively means we must compile the virus code as position independent that we talked about in the previous videos. Modern GCC does that automatically, but it can double ensure that by passing the -fpic flag when you build the code. If you look at an example host binary layout on the right, you can either inject the virus inside the gaps between these sections, or even append to the end of some sections. But this file layout will be entirely different for each executable you wish to infect. That's why we need to make our virus position independent, because we want them to work for different executables. You can verify that the virus is position independent by checking if the ELF header says it's a shared object. The second thing is that our virus must be self-contained. It doesn't have the luxury of using dynamic linking. We talked about how libraries are dynamically loaded into a process address space by the program interpreter in the past. The picture on the right shows an example executable address space. Whenever we want to call a function from an external library, we can simply jump to the external library segment whose address is resolved by the program interpreter. But inside our virus, there's no way to tell the kernel that we need to load external libraries. The kernel simply doesn't know what our virus needs at runtime. Therefore, it is a requirement that the virus must be statically linked, and it must have all the code it needs right inside its .text section. You might think this is not a big problem because you can still use your favorite open source libraries as long as it's statically linked. But that will increase your virus code size by a lot, and a bigger virus means it's less likely to survive undetected. In fact, some infection algorithm is very picky about the size of the virus. If it's too big, we'll not be able to spread effectively, and this is a trade-off you need to think about. What about libc, the most common library? Unfortunately, we cannot use it because it internally contains global variables that reside in the .data section. Let's take a look at an example virus executable file layout after compilation on the right. If our virus uses global variables, that means the code in the .text section would need read and write access to things in the .data section. This means we would need to carefully inject both the text and data section of a virus into a place that has the right permission, at the same time maintaining the same offset from each other. For example, say this red arrow indicates that we want to read a global variable in the data section. The assembly instruction generated is equivalent to load some bytes as some offset from the calling instruction. Say the load instruction is at address 0xab that says we need to load a global variable at 0xffab. This instruction will only encode the relative offset 0xff00 from the current position to locate the variable at 0xffab. It's non-trivial to inject this virus into arbitrary executables, as it's very unlikely that we can find a good location for both .text and .data sections that has the right access permissions while maintaining the same relative offset. Imagine if the .data section is injected into a random place. The original instruction in the .text section can no longer use this offset 0xff00 to find a global variable. Therefore, we simply avoid the use of global variables altogether. glibc cannot be used because internally it has global variables such as error number. The way to work around this is to implement our own version of the libc. The virus framework I talked about earlier in the course provides a tailored version just for virus writing. You can go to the repo and see the source under no-std-lib folder. In summary, the virus must not use global variables, which could complicate infection later. You can disable linking the default libc by providing the options listed above. Welcome back. Last time, we discussed that a virus cannot use global variables because we want to avoid injecting the data section of a virus into a binary we want to infect. In this video, we'll talk about limitations for RO data. Whenever you use a string literal, it's automatically put inside of RO data section. If our virus uses a string literal, we will need to inject both text and RO data sections into binaries we wish to infect. This sounds like a similar problem as the global variables in the previous video. Some syscalls, like read or write, require initialized strings for their arguments. You might think, why do we create a string on a stack without touching our data section? Our compiler is smart enough to know that this array on a stack is used in a read-only manner and will automatically move it to the RO data section. Our virus framework provides two mechanisms to work around this. The first approach is to combine the .text and RO data sections into a single blob so that they can be injected together. Because .text section is usually injected into a place that has both read and executable permission, we can piggyback the RO data section onto the text section while maintaining the same offset. We have a smaller problem than injecting the data section since we don't require write access for RO data. However, you need to be very careful to not use too many string literals as it can increase the virus size. Another approach is to force the compiler to put strings into the text section. Let's take a look how it achieves that. Here we have two macros for x86 and ARM. Let's take a look at the x86 version first. This macro is called string literal, and you can see how it's used by our example test virus. Let's follow the arrow on the screen. We define a C++ lambda that is immediately executed. This tells the compiler that the code here will be inserted into wherever it's called. For example, the main function on the right, and since the main function is in text section, our generated string literal is also in the text section. We then define a local variable that captures the string literal address, which will be later returned to our caller. We start using inline assembly here by loading the effective address of label 1 into our local variable. You can find the label 1 right below the jump instruction. By defining an array of ASCII characters after label 1, the address of label 1 is the same as our string literal specified by the caller. We essentially tell the compiler to generate the string right here at this location. After loading the address of the string, we jump to label 3, which skips executing everything in between. Our string literal is not valid instruction, and our program will crash if we run it. The inline assembly finishes, and we return the string literal address to the caller. You can verify that our string literal is generated right inside the .text section using objdump. You should be able to see that the string is mixed together with instructions on the right. I'll skip over the ARM implementation because it's very similar, with the exception that it requires some extra padding for alignment since ARM instructions are fixed length. This approach removes the need to access RO data section within our virus by sticking strings inside the text sections. But the boilerplate here could waste a little bit of a space, which is around 9 bytes on x86 and 8 bytes plus padding on ARM for a single string. Also, if the same string literal is used in different places, they will be generated multiple times. So use this carefully to avoid increasing virus size. In summary, we talked about constraints in writing virus code and ways to work around them. You can see that it's very hard to write a virus as you must get all these things right. This is where the virus framework aims to solve. It provides unit tests, gen rules during the build process so that we can be sure that our virus will work, and we can focus on the virus logic itself. In the repo, there are some sample viruses for you to play around under the virus folder. You can see examples on how to transmit data over sockets, create reverse shells, which I think is more interesting than printing hello world. In the upcoming videos, we'll take a look at the considerations for linking the virus. Hello and welcome back. I think it's a good time to give you a high-level overview of the virus framework so that you can understand the structure of the repository and where to find the implementation that we've been talking about for this course. If you have followed the setup video, we have cloned the repo in this VF folder inside your home directory. I'm going to use VS Code to show you the structure of the repository. Let's look at these folders one by one. The first one is the Circle CI folder that contains a configuration file for CI jobs. Every time a commit is pushed, we'll run all the unit tests for both x86 and ARM so that we can be sure the infrastructure is working. The common folder contains useful C++ classes or helpers that you can use in your virus code. For example, it has this directory iterator that you can use to loop through all files in a directory, or even recursively. It has a file descriptor class that opens up a file descriptor during construction and also closes it automatically for you. And this is my favorite C++ feature. One thing worth noting is that even though we have an implementation of the string class in this folder, it is not recommended unless you absolutely have to manipulate strings, because it will make your virus much bigger. The infector folder contains 3 different algorithms that you can use to inject your virus into an arbitrary binary, and we'll talk about them in details later in the course. The NoSTDlib folder contains a version of the libc that is tailored for virus writing. It contains all kinds of useful functions that you would typically find in GNU libc. For example, this read function, and let's see how it's implemented internally. This read function calls a sysread function inside and forwards all arguments to it. The sysread function issues a syscall and forwards all the arguments to it. And the syscall is basically a wrapper for an inline assembly. As you can see here, svc0 is the way that we issue syscall on ARM. If something goes wrong, we do not set error number because we cannot use global variables. We simply return the results to our users. The list of functions here are not exhaustive, and we can add more if there's a use case. But it looks like we already have enough functions to build a virus with. This folder also contains a Bazel rule that specifies how viruses are built. If this is your first time to see the Bazel syntax, don't be scared. It's very similar to Python. Here, we provide a list of useful compiler flags so that we can turn off unused features to prevent compilers from generating unnecessary instructions. For example, the exceptions, frame pointers, stack protectors, and unwind tables. We also optimize for size because the code size for a virus is very important. And lastly, we enforce that our virus is built as position-independent code. Every time you write a virus, you should be using this NoSTDlib binary rule because it encapsulates the entire pipeline for building a virus. It first tells the compiler that we should be using all the link options or compiler flags to build our virus, and also we supply our own version of the linker script as well as the startup code. After the virus is built, we generate a Python test that can look inside the compiled virus to ensure that it doesn't contain sections that we do not want. For example, the .data section. If the virus is valid, we have a gen rule at the end to extract the text section of the virus into a binary blob so that it can be injected into other binaries. You can find the customized linker script in this folder as well that arranges the virus binary layout in a way that we want it to be. And of course, we have our own startup code that replaces the CRT0. The propagation folder provides a helper that you can use to spread the virus into other binaries. The redirection folder provides 2 algorithms to hijack the control flow of the host binary so that we can run our virus first and then our host binary. The signature folder contains a simple way to stamp a binary so that we do not recursively infect it over and over again. You should be very familiar with this mechanism because this is what we did manually in our first lab. We have a lot of code for test support because writing virus is very engaged and we want to make sure that our code works as expected. The third-party folder contains documentations from other people because articles talking about virus techniques tend to disappear, and I think it might be a good idea to cache them here. And we use PyTest for this repository. The virus folder contains samples that you can use as examples to craft your own virus. For example, we showcase how to use sockets or even write a reverse shell. If you want to write your own virus, you can copy the example here and then change the name to your virus. The name of the virus must be unique so that our build system can identify it. You should also put your source file inside this sources list. The dependency list captures all the libraries you use for your virus. For example, we're using macros here as well as several libc libraries. You can change this list based on your virus. And that's pretty much it. Rest of the files are not that important, except that Docker file that we use to set up our dev containers. If you use the repo here for your research, you can cite the work here as well. I'm open to accept PRs if you think there are ways to improve this framework or there are new algorithms that is worth implementing. Just one more thing I want to cover before we wrap up. This repository is cloned on your local machine, and it is also available inside your development containers. Any modifications you do on your host machine will be immediately visible to your dev machine so that you can build and test the code you changed. I hope you find this video useful to help you get started and experiment on your own. Welcome back. Previously, we talked about some of the challenges when writing virus code and ways that we can work around them, which is the first block on the diagram above. In this video, we will talk about steps you need to take when linking the virus code. To put it simply, linking is a step that connects small parts of the program that are compiled separately into a single executable. Let's review how a normal software runs. Upon executing a binary, the kernel prepares the address space and then starts executing code from the elf entry point. The entry point contains a label called _start that is provided by the C runtime CRT0 linked by the linker automatically. The CRT0 sets up the environment and then we will run the main function. Imagine you somehow infected this binary with a virus, and we want to run the virus every time this infected binary runs. Once the virus has finished, we need to resume executing the infected binary. What would the execution flow look like? On the right, you can see that we have 2 extra red blocks inserted. The virus is just code, and it's got its own main function like what we did in the test virus. There will be problems if we link the default CRT0 startup code for our virus. First, we will be running the same setup code again when we are done running the virus. The program will likely crash because the setup code has certain side effects, like changing the stack or register contents. Second, linking the default CRT0 can increase virus code size. On my ARM Linux, it's about a couple kilobytes of additional code. Our virus only needs the bare minimal setup to execute its main function. The execution flow on the right is what we will see once a binary is successfully infected. So far, we haven't talked about how these blocks are inserted, but later you will learn the techniques used to redirect the entry point to run our virus and how to get back to the infected binary once the virus is done running. You can find the default startup code via the link above. It's too long to fit on one screen, which you can kind of get the idea why our virus doesn't need most of it. The assembler code below is our version of the startup code, which is very concise. I'm showing the ARM version, but x86 is very similar, and you can find both of them in the virus framework repo under the no-stdlib folder. Don't worry about memorizing the syntax here. I will guide you through it. We first tell the linker that we want to put the code here in a special place inside the text section that's called text.startParasite. It belongs to the text section, and we conveniently place it right before other text sections. Ensuring the order here allows us to extract virus code as a continuous blob easily later. Then we define a global symbol _start, following the convention of other normal programs. As soon as the linker sees this _start label, it will fill in the address of this label inside the elf header's entry point. This is essentially saying, execute from this instruction when the virus runs. Right below, we have a whole bunch of store instructions that copy the contents of important registers onto our stack using the STP instructions. This is required since we want to preserve the register states and later restore them by the LDP load instructions. To use an analogy, we're borrowing the infected program's scratchpad to operate our virus first, and after we're done running virus's main function, we will need to restore everything back and pretend nothing has happened. You can see the main function runs in between, and this is the main function of our virus. How do we jump back to the host program and continue its execution? This startup code has left an invalid instruction 0x11223344 that can be patched when infecting a binary. This is because we only know where to continue the execution flow at infection time. In other words, when we infect a specific binary, we will parse the elf header and locate the original entry point, then fill in the return address here that can be different for each binary we wish to infect. On ARM, the instruction is 4 bytes long, and we have just left enough space for an unconditional jump instruction. The _patch return is a global label that allows the infection algorithm to easily locate this place so that it can patch the address. Referring to the diagram you saw earlier, this is how we achieve the yellow arrow here and continue running the infected program. The CRT0 of the original program should not be aware of anything that we have done, and that's how we run the virus in stealth. In summary, we look at our own version of the startup code that provides the required _start label as the entry point for our virus. Since we don't need most of the setup from CRT0, we have achieved great code space saving as long as we have restored the registers to their original state. After running virus code, this startup file also allows us to jump back to the infected binary and resume execution there through address patching. We will see more in detail how patching is done later. In the next video, we'll look at another custom building block for our virus, the linker script. Welcome back. Last time, we looked at the custom startup code, which acts as an entry point for our virus. We'll talk about another custom building block, the linker script. When you dump the section headers for a program, you will see it contain lots of sections. For example, the interpreter, symbol hash, and dynamic linking sections are the most common ones, as well as the text sections in the middle. For each of these sections, it has a file offset and size that describe where you can locate code for them. So how does linker know the order of these sections? For example, can we generate a valid elf that has data section right after RO data section? And this is where the linker script comes in. For the sake of illustration, let's dump the section headers for our test virus, which has significantly less number of sections. We use a custom linker script to order and combine sections for our virus so that all the code can reside in text section and can be extracted together as a binary blob. The linker script is written in its own language. You can think of it as a file with a collection of linker commands. The entry command tells the linker that somewhere in the code has a _start symbol, and we should use that as the elf entry point. If you remember from the previous video talking about the startup code, it comes from there. Immediately after the entry point, we define a giant block of sections command that specify the order of all sections. The beginning of the block captures a list of commonly generated sections you would find in most executables and put them together right next to each other. They have no use for our virus, since some of them are for dynamic linking. These sections can still be generated even if we do not use them. So it's best to be explicit about the layout order. On the left, you can see for our test virus, these unused sections have 0 bytes filled in since we do not use them, but they're still part of the file. Then we have a big text block that describes the order for code sections. This allows us to order code even within the text section. For example, this start parasite section, which was used to move our custom startup code as the first block in the text section. Rest of the entries in this list capture common variants of the section naming so that they all appear after our virus startup code. Right after the text section, we tell the linker to put the RO data section there. This is because sometimes we may want to merge both text and RO data and extract them as a whole blob. You can ignore the GOT section below for this discussion. You might wonder what these lines are for. The dot command means we will assign the current address to a symbol. This tells the linker to record the start and end offset of our virus and expose them as symbols that can be used to calculate how big our virus is. During infection, our algorithm will need this information in order to find an appropriate place to inject the virus. Let me summarize why we need to use a custom linker script. We need to first tell the linker what the entry point is. In our case, it's supplied by our startup code you saw in the previous video. Because a compiled executable can have various sections that are unused by our virus, we'll need to put them in one continuous block that can be ignored altogether. For the text section, we want it to contain all code for the virus, including our startup code that needs to be run first. We'll need to make it the first section within the text section. When we inject the text section of the virus, we can assume that the first instruction is the entry point. For some viruses that need to reference RO data, we place it right after the text section so it's easy to extract them as a single blob. Lastly, our linker script exposes a way for effective algorithms to query how big a virus is. Both the linker script and the startup code must work hand in hand to achieve the optimal structure for our virus. They are passed to the linker as arguments during the linking process. You can find the source for this linker script in the virus framework repo under folder no_stdlib. Next, we will take a look at how we extract the virus code into a binary blob. Hello there! We've discussed constraints and workarounds when writing code for a virus, as well as important pieces used during the linking process. In this video, I want to show you how to extract and prepare the virus in a form that is ready to be injected to other binaries. This is the last step of this pipeline. First, let's make sure our development container is up and running. Then let's connect to it. Let's use the test virus you saw before as an example. It simply prints out running virus code 1 and then exits. You can find the source code for this test virus under the virus folder. Let's build it. The compiled virus is saved in the temp folder. Our test virus is a valid ELF executable that is compiled as position-independent code. It has section headers as well as program headers. In total, it has 8 sections. We can dump the contents of these sections using the objdump command. The -s option gives you some sort of hex dump for each section. Because our virus does not use dynamic linking, most of the sections here are empty because they are not used. At the very bottom, it has this common section that is automatically filled in by our compiler. It captures the clang compiler version as well as the linker version. But this has nothing to do with our virus. Obviously, we don't want to carry all these weight around. That's why we need a process to extract the text section of our virus. And this is the only section that matters. You can achieve this with the objcopy command. The -j option specifies the section we want to extract. The -o option specifies the output format, and in our case, we want the raw binary output. Then we specify the input file, which is our test virus, followed by the output file name. We can dump the contents of this extracted binary file. This file starts with E007 and ends with 5FD6, which is the same as our text section. There you have it. This binary blob contains our virus code and is ready to be injected into other executables. Our framework does this automatically for you, so you don't need to run the command manually. We have a basal rule under the folder nostdlib, and this nostdlib binary rule wraps the entire build process. It first tells the compiler that we need to use some custom building blocks such as the linker script and the startup code. And then it generates a PyTest to ensure that our compiled virus is valid and can be injected. Then, at the very end, we use a gen rule to extract the text section. You can run the gen rule by appending _text only to our virus name. Now the extracted text section is saved in the temp directory. We can dump the contents using the hex dump tool. The output is exactly the same as what we have when we did it manually. Good day, folks. In the previous section, we discussed the challenges of building a working virus and how to overcome them. The build process gives us a binary blob containing our virus code, but the ultimate goal is to inject the virus and run whenever the infected binary runs. In the following videos, we will explore 3 different algorithms that can find a suitable place for our virus within an infected binary. Here is a high-level overview of the infection process. Given an arbitrary executable, we want to infect it with our built virus. The first step is to scan the host executable to determine its eligibility for infection. We need to ensure the file is genuinely an executable and filter out other file types by parsing the ELF header. Remember, all ELF files contain a magic array that identifies them. If our virus targets 64-bit Linux, we should probably skip 32-bit ones, as it's challenging to craft a virus that can infect both simultaneously. Although most people use 64-bit Linux now, 32-bit viruses are rare but still possible, especially targeting 32-bit embedded systems or Internet of Things devices. If an executable is eligible for infection, we make a copy of it, which will replace the original once all modifications are done. Next, we scan the file for its section and program headers, parsing them to find a suitable place for our virus. If the infection algorithm finds an appropriate spot, the section and program headers will be updated to accommodate the virus. For instance, if we piggyback our virus onto an existing section, we will need to increase the section size and possibly make other changes to shift things around. The final step is to copy the virus into the identified place, byte by byte. The changes are committed to the copy, and then the original executable is replaced by this modified version. In the following videos, we will introduce 3 different algorithms, each with its own trade-offs and use cases. Regardless of the method we use, the high-level workflow remains the same. Our virus framework includes working versions of these algorithms and the integration tests to infect popular Linux distributions. You can find them inside the Infector folder, and I will see you next time. Welcome! In the previous section, we discussed the high-level steps for infecting an executable with our virus. Now, let's dive into the specific algorithm for finding an appropriate place for our virus within the target binary. This first method was proposed by Silvio Cesare. You can find his original paper and proof of concept code in the third-party folder of our virus framework repository. The entire virus framework began because I wanted to implement this infection technique myself, and it has been a significant inspiration for me. Although the original paper and code targeted 32-bit Unix operating systems, I've made it work for modern 64-bit Linux systems on both PIE and non-PIE executables. The fundamental flaw this method exploits still exists, so the paper's content remains valid. Before we talk about the algorithm, let's review the ELF header and loading process. You can dump the program header with readelf using the -L option. The table we're looking at contains 2 load entries, which means the operating system will load 2 segments from this executable file into memory. The first segment is readable and executable, denoted by letters R and E in the flag column. This segment probably contains the text section that requires execution permission. The second segment probably contains our data section, since it's both readable and writable. We talked about this virtual address column in the past, which denotes the offset of where a segment starts from the address that is randomly chosen by our kernel in order to make certain memory bugs hard to exploit. Let's say the starting address is 0xFF00000. The offset for our executable segment is 0, which is where the first arrow is pointing at. We construct this segment beginning at this address. You can find the segment size pointed to by the second red arrow. If you add the size to the start address, you will get the ending address of the segment, which is 0xFF06E00 when you sum them up. Likewise, we can calculate the starting address for our readable and writable segment by summing the initial starting address 0xFF00000 and the offset pointed to by arrow 3. Now, let's focus on the end of the first segment and the start of the second segment. There is a huge gap in between. Recall that the minimal granularity of memory access control for our operating system is a page, which is around 4 kilobytes. Our kernel will actually map extra bytes at the end of this segment all the way until the current page boundary. The yellow box shows the extra bytes the kernel mapped at the end of the executable segment that are not used by anything. You can calculate the yellow boundary by rounding up the segment end address. This extra space is what we call code cave. It's a place that exists in memory since the kernel maps it, but not really used by anything. It is a perfect place for our virus as it already has executable permission. If you do the math, we can fit at most one page size of virus code there. This algorithm is quite straightforward. It relies on the fact that the memory access control granularity must be a multiple of page size. I want you to look at a couple other executables and get a feeling of how common this padding occurs. The one on the top is the ls binary that people commonly use. If you follow the math on the right, which skips the initial address as we only care about the difference in the ending address, the gap size is around 3200 bytes. We almost have the entire page for the virus. The bottom is the GCC compiler, which for some reason was not compiled as position-independent code, but it still contains the code cave with around 250 bytes. I suggest you go to your development container, pick some random executables, and calculate the gap size on your own. I'm showing binaries on my ARM container, but you might see a different layout in the x86 container due to the fact that the default linker script for different architecture might vary. Now that we understand the core concept of this injection algorithm, which looks for a code cave at the end of the executable segment, how do we actually inject the virus? The first step is to find the executable segment. Almost all ELF binaries have a single executable segment because there's no good reason to break executable code apart in memory. If you see multiple executable segments, that could be a sign of virus infection and you should be very cautious. Next, calculate the ending address by adding the segment file offset and file size together. This ending address is where our virus would live in. You can then round the ending address to page boundary and calculate the gap size to see if the code cave can accommodate the virus. Then, we'll update the program header for this segment to increase the file size field, which tells kernel how many bytes to copy from the infected executable to memory, and the mem size field, which tells the kernel how big the segment is in memory. Then, we will need to find the last section belonging to this executable segment by comparing the addresses of sections with the segment address. In the example on the right, it's the GCC except table section because it is the last section that has the file offset start before the segment ending address. Our virus framework has tools that you can quickly test inside the development container that infects all binaries in a given directory. This is what you saw in the demo at the very beginning of this course. The command you can run to build the test virus as well as the infection algorithm is listed above. This infector tool makes a copy of the original executable and then infects them with our test virus. After infection, it checks the output to ensure our virus code runs first and then the infected binary without crashing. I'd say it's quite satisfying to see this algorithm run in action and achieve a very high success rate. In summary, we introduced the first infection algorithm that takes advantage of code segment padding due to the memory access control boundary must be a multiple of page size. A virus can be injected into this padding, and we looked at what needs to be done to update the ELF header to accommodate the virus. The infected binary is a completely valid executable and it can still function like it always did. Hello and welcome back. The text padding infection algorithm was introduced in the last video. It relies on the padding at the end of the text segment that is mapped by the kernel. The extra space has executable permission even though it's not used by anything at all. I want to show you the algorithm in action and compare the file structure before and after infection. First, let's ensure our Docker development container is up and running. Then, let's connect to it. In case you haven't tried the command from the last video yourself, I recommend you to follow along. We will use this command to build all virus code under the virus folder, as well as the infector tool that we use. Let's infect a single binary, the ls tool that comes with most Linux distribution. We can achieve this by invoking the infect victim script. The first argument is the text section that was extracted by our virus framework. The second argument is the infector tool itself. The third argument is the infection algorithm we'll be using, and in this case is the text padding algorithm. Then we specify the entry point redirection algorithm that we'll talk about later in the course. The last argument is the binary path that we will infect. Our infector will inject the virus and run the binary immediately with --help option. It looks like we have successfully performed the infection because the ls command is printing running virus code 1. The original ls command still runs, and this is what you would see when you pass the --help option. The infected copy is saved to the temp directory and is named as victim. Let's dump the elf headers of the infected victim binary into a file. And then let's also dump the original ls command into another file so we can compare the difference. The red lines are from the infected version, while the green lines are from the original. The very first thing you notice is the difference in the elf header padding. We inserted 2 extra bytes as our infection signature. This is what we did manually in the first lab. We also have a different entry point address. Because we want to run our virus first before the infected binary, the elf entry point was modified so our kernel will start running from there. Later in the course, we will talk about how redirection works in detail. The error handling frame section was also modified with a bigger size. It needs to reflect the original section size plus the virus size. Lastly, the executable segment's program header has a new size as well, which represents how big the segment is in memory. The increase is also used to accommodate our virus in memory. If you look at this number 0x1c490, it is the file offset of where this section starts. We have injected our virus right after this section, and that's why we increase the size here, pretending that our virus is part of this section. Let's see what the original file looks like at this location for this section. Your favorite tool, hexdump, takes an offset argument with -s that can show the contents of a file starting from that position. What you see here is the hexdump for this error handling frame section. This section is used to handle program exceptions and call frame information that will be used during unwinding. If we scroll down to the end of this section, we will see a giant blob of empty void. This is the code cave we've been talking about. It not only exists in a file, but is also mapped into memory as is. The end of this section is around 1F360, And let's remember this number. If we dump the victim binary, we should be able to see similar structure there. Here is our familiar blob of virus code that prints running virus code 1 onto the screen. Our text padding infection algorithm did its job, and it has this nice property of not changing the binary size as it overwrites 0 bytes with our virus code. This algorithm is simpler than other algorithms, which requires shifting of some sections. I hope this video gives you some intuition, and we will do a quick overview of the implementation in the next video. Hello there! Last time we looked at the file structure difference before and after an infection and saw how different fields in the ELF headers have changed. Also, we demonstrated that the virus was injected into the text segment padding at the end. I want to show you the code that made this all work. Let's navigate to the infected directory where we keep all the infection algorithms. The one we used is called padding infector. It's a simple class with only 3 public APIs. The injected host size function tells you how big the file is after a successful injection. In our case, this algorithm doesn't change the file size because it simply overwrites a bunch of 0 bytes in the ELF file as we saw last time. This function could be different if the algorithm, say, extends the segment or adds a new segment to accommodate the virus. The analyze function returns a boolean denoting whether an executable is suitable for infection. It checks sections and program headers to figure out how much padding space we have and if it's big enough for our virus. It takes a span of bytes for the host binary as well as the virus, so the caller is responsible for preparing the file buffers. During the analysis stage, we do not do any modification, but instead crunch some numbers that will be used for the injection function. The inject function performs the infection and returns the infection result that could be used by redirection algorithms, which we will introduce in the next chapter. This 3-function interface is shared across all infection algorithms for the PT node infector, as well as the reverse text infector. Let's go over the source of the padding infection. The analyze function rejects files that are not executable or a 32-bit by returning false to the caller so we can stop early without damaging the file. This ELF64 header structure is what you saw earlier in the course from the ELF manual, which explains all these fields pretty well. The E-type field specifies the type of the binary. We cannot infect other ELF types, such as a core dump file. This ident array tells us if it's a binary compiled for 64-bit CPUs. We then iterate through all program headers one by one. The goal of this loop is to find the executable segment and see how big the padding at the end is. As soon as we see one with executable and read permission, we record the ending position of this segment. And it is a potential place for a virus to live in. If you read the comments, for this infection to work on ARM chips, we will need to do some alignment checks so the virus we inserted starts at an address that is a multiple of 4. Then we continue the loop and find the next segment right after the executable segment, because we'll need to use the starting position to subtract the ending position of the executable segment in order to calculate the padding space. This line does exactly that, and we return false if it cannot fit the virus. Then we cache the index of the executable segment so we can later modify it. Let's look at the infect function. It does three things in sequence. First, it patches the program header for the executable segment that we previously found. This patch program header function basically increases the size of the segment to account for our virus. Then we patch the section header. Remember, we insert our virus to the end of the executable segment, so here we need to find the last section within the executable segment. This loop looks at all section headers and compares the file offset of each section to the executable segment's ending position. The one we're looking at must have the same ending offsets. Then, this section is extended in size to account for the virus. After all headers are patched, we copy our virus into the file and return some useful information to the caller. The position to inject the virus was previously calculated by the analyze function. There you have it. This file is pretty well documented, and I hope it's much easier to read after you have gained some intuition of how this algorithm works. Since this is our first time looking at the infector folder, I want to quickly mention some other infrastructure we have. The common infection file contains free functions that handle copying the host binary, calling the injection class, and replacing the original with our infected version. The infect victim script allows us to infect all binaries in the directory, and this is what we use in the demo at the beginning of the course. We also have integration tests that runs all our infection algorithms inside Docker containers for popular Linux distributions. For now, we run it in Ubuntu 18, 20, and 22. You can see how this is done in the infector.bazel file. Next time, we will introduce another algorithm that reversely extends the executable segment to inject the virus. Hello and welcome back. We have studied how the text padding algorithm works previously, which injects virus code right behind the executable segment using the padding space. In this video, I will introduce another infection method that was proposed by Silvio's original text padding infection paper. He didn't provide a prototype, but I have implemented a working version inside the infector directory of our virus framework. This algorithm is called reverse text segment infection. The picture on the right demonstrates a simple memory layout with addresses growing downward. Previously, the text padding infection injects a virus into the padding between the executable segment and the segment after it, with the virus having a higher memory address than the executable segment. This algorithm extends the executable segment in reverse direction to make extra space for the virus. In other words, it extends the segment in lower address direction, and that's why it's called reverse text infection. It's quite amazing how people would come up with different ways to take advantage of things in order to inject a virus. Let's first observe the program headers of some example binaries on our development containers. These two pictures come from the GCC and AR tools that are part of the compiler toolchain commonly used. They're both non-PIEs, as the type is executable file. One special thing about non-PIEs is that the virtual address column for this table denotes the absolute address in memory where segments will be loaded. In other words, we will be able to deterministically locate a segment for an executable using addresses here. Just to remind you, this column encodes address offsets for PIEs, and the actual location of segments will randomly change by our kernel to make certain types of memory bugs hard to exploit. It turns out that non-PIEs almost always use this address 0x4000 00 by default. People start to think, the space before this address in memory is not used. Why not inject a virus in there? That is the essence of this reverse text segment infection algorithm. The space available for our virus is huge when you subtract 0 from 0x400000. It's roughly 4 megabytes. Compared to the text padding infection, which can at most inject 4 kilobytes, we have a lot more space here. However, this reverse text infection only works for non-PIEs, as this fixed starting address is only used for non-PIEs. Luckily, modern compilers by default compile executables to be position independent, which makes them immune to this infection. I think as time goes by, this algorithm would slowly fade into a history book, but I still want to mention it for the sake of education and show you this interesting exploit that was pretty impactful back in the days when most things were compiled as non-PIEs. The skills to make this work could be useful for devising your own algorithm. Now that we understand where the virus lives in memory, let's discuss where we inject that virus into the file. The most difficult part for this algorithm is the handling of section shifting. The choice is to inject the virus right after the elf header. The elf header must be the first thing in the file, starting with a 0 offset, because that's where the kernel thinks it should be. When the virus is injected, we must shift all sections that come after it by the same amount of offset. If there are any internal data structures recording the section offsets, we will need to adjust those as well. This includes all entries in the dynamic section if a binary is dynamically linked. Some entries need, for example, to find a file offset of GNU hash section for fast symbol lookup. The same thing is also applied to the program headers. We must shift file offsets for each entry to accommodate inserted virus. Let's look at the file structure before and after an infection for our GCC executable. The red one is post-infection header. One observation is that pretty much all section headers file offset has been shifted back by 2 pages. Another thing is, these sections are mapped to exact same location in memory. If you think about it, since we're extending the text segment backwards, the original code in memory shouldn't really change. The file offset changed due to the fact that we need space for our virus. This technique essentially shows us that where sections are located in the file has very little to do with where they live in memory. In fact, the ELF standard only states that the start of the section must be a multiple of page size, and we kind of took advantage of this to shift things around. The same thing applies to program headers as well. The file offset of segments are shifted back by 2 pages. While we keep the memory address of most segments intact, the executable segment was extended into lower addresses. This extension allows the virus to be loaded into memory without touching memory addresses of other segments. In summary, we introduced the reverse text infection algorithm that takes advantage of the fact that non-PIEs always start their segments at a fixed address. Compared to the text padding algorithm, this method allows us to inject a larger virus. One downside is that it only works for non-PIEs. We also look at how to shift parts of the file structure to accommodate the virus, both in memory and in the file layout. I hope you get a sense of this idea of doing file surgery that is essential to any kinds of infection algorithms. Likewise, you can find a well-documented implementation in the injector folder. In the next video, we'll walk through the implementation together. Hello! In this video, we'll look at the code for the reverse text infector class. You can find the implementation under the infector folder. There's a little essay here documenting various challenges that we have to overcome. Initially, I read Silvio's paper and I thought it would be just as easy as the text padding infection. I was very wrong and spent a long time to make it work. Because our virus framework promises that everything here would work for both x86 and ARM, It made the implementation even harder due to ARM's alignment requirements and a slightly different executable layout. But here we are. Since it's pretty well documented, I'm just going to go over it very quickly and point out major pieces you need to be aware of. This class follows the convention of this analyze and then inject API that allows us to abort early. The injected host size function tells us how big the infected binary would be. Because we're inserting a virus and shifting all sections, the file size will increase. This padded virus size is calculated during the analysis phase. The majority of the code here is similar to text padding infection, and we iterate through all program headers to locate the executable segment. Perhaps I should extract the code into a common library and reuse it here. Once the executable segment is located, we calculate the padded virus size. We need this extra padding in order to make it work for ARM. This parasite load address is where the virus will be loaded into memory after we reversely extend the text segment. You notice that we compare this with the minimal address from mmap syscall. This minimal address restriction is something that our kernel provides to protect us from certain bugs, such as dereferencing a null pointer, but the default minimal address is 0. If we perform infection on some systems that have a larger value, it means we might not be able to use up all 4 megabytes of the space for our virus. This block of code is used to handle the default ELF layout on ARM, and we will need to pad it with an extra page. If everything works out, we'll perform the injection. The injection consists of 5 steps. We first patch the dynamic section by iterating through all entries that could be referencing section file offsets. Remember, once we shift sections, these links will also get updated. Then, we patch the program header by shifting file offsets for all segments and reversely extend the executable segment. In the patch section header function, we loop through all section headers and shift the file offsets there. After that, we update the ELF header to reflect the new file position where we can find the program as well as section header tables. They were also shifted together with sections as the virus was inserted before them in position. Lastly, this inject virus function performs memcopy to insert the virus into the file at the location we previously calculated. You can perform this infection with the following command by specifying the reverse text algorithm in the argument. Since this algorithm only works on non-PIEs, the success rate is pretty low, but nonetheless, it works. Interesting. It looks like we were able to infect the Python interpreter. Let's see if we can run a virus every time we run Python code. Let's write a simple Python script. And then let's infect the Python interpreter. It looks like the infection is successful, and we have made a copy of the Python interpreter in the temp directory. Now let's run the victim Python interpreter. This is pretty cool. Regardless what Python script we run, we can sneak in our virus code to run first. Imagine this virus is more sophisticated than printing hello world. It can steal user data and send them back to a command center, or even open up a reverse shell in a forked process. I encourage you to try it yourself and play around with this infect victim script, and I will see you next time. Welcome back. Previously, we talked about the reverse text segment infection technique that extends the text segment in lower memory address direction, a place that is not used by anything. It is able to fit a comparatively large virus than the text padding infection, but unfortunately, it only works on non-PIEs. We also read the code together and show you pretty complicated steps to perform surgery on ELF structure to make it work, since almost all references to section file offsets will need to be updated. In this video, we'll introduce a somewhat simpler algorithm that converts the PT note segment into a place for our virus. It's worth mentioning that it has almost 100% success rate. We've looked at program headers many times now and introduced new details as we go. You probably have noticed that each program header has a type. The PT note is referring to this note entry in the picture above. According to the section to segment mapping, this note segment contains two sections, the GNU build ID and ABI tag. These sections contain static info about this executable, like a unique ID that can identify this binary and compatibility information that is important for some applications if they're compiled for a specific version of the kernel. The ELF manual has a nice section about the segment type here. It's basically a special type for these note sections, and the PT load type is for executable, read-only, or read-write segments that we have previously paid a lot of attention to. The algorithm we will talk about today converts the PT note segment into a PT load type by taking advantage of the fact that most executables do not care about these note sections at all. The modified PT note segment will then point to our injected virus with executable permission. I first encountered this method from an online article which states that it works on non-PIE executables. I have since improved it and implemented a working version for both PIE and non-PIE in our virus framework repo. This algorithm has the highest infection success rate compared to the two other methods we've talked about. Here is how it works. We will simply append the virus code at the end of the ELF file. Compared to the reverse text infection, we do not need to do any shifting since section file offsets are unchanged and the complexity in implementation is way less. In memory, we will also tell the kernel to load the virus at an address that is higher than any other existing segments. All we need to do is to adjust the original note sections and program headers to record these new locations. Let's take a look at what changed before and after an infection. This red line shows what's changed post-infection, and the green is pre-infection. We literally repurposed the original GNU build ID section inside the PT note segment for our virus to use. The first column of numbers is for virtual memory address, which is where the section should be loaded in memory. There's an increase since our virus will use the largest address out of all segments, and that's why we end up with a rather large number 0x940000 here. The second column corresponds to the file position. Since we're appending the virus to the end of the file, we also expect a fairly large offset change. Due to some alignment requirements, this offset is also padded to a multiple of page size. The third column records the virus size, and then we added executable permission for this section as we want to run the virus. Lastly, the alignment for this section is updated to a number that is used by other executable sections. This is not typically required according to my experiments, but I changed it just to be consistent with other sections. Likewise, the modification for the program header is also straightforward. First, we change the note type into the load type that is used by an executable segment. Then, we do the same modification to file offset, memory address, virus size, and permission. These values are exactly the same as what we used for the section header entry we modified. Similarly, the segment alignment is updated to what was used by other executable segments. Because of the change in file offsets and memory address, the section to segment mapping at the bottom also changed. You can basically ignore that since it's just for our information. The original note segment is repurposed into an executable segment for our virus. I want you to be aware of some of the downsides. First, this section we're repurposing are used by binaries compiled from Go. It actually contains useful information that is needed at runtime. The Docker binaries note section has a description data array, as you can see. I'm not sure what it contains, but in my experience, if we modify it, the binary will be damaged. Another thing is, if you look at this program header from 1,000 feet above, it has two segments with executable permission. There is no good reason to separate executable code into two different segments with vastly different memory addresses. You should scream for help if you ever see this on any executables, because it could be a sign of infection either by this PT note algorithm or some other variance that adds a new executable segment without touching the PT note segment. In summary, we've introduced a new infection algorithm that injects a virus to the end of the file and pretending to be one of the GNU note sections. The implementation is pretty simple, as the modification required is not as involved as two other algorithms we've talked about. Next time, let's look at the code together. Hi, we introduced the PT note infection algorithm last time, which is a very powerful method that repurposes a note section for our virus. Let's take a look how it's implemented. You can find the source under the infector folder from the virus framework repo. This block of comment here just reminds you that we need to detect and skip infecting Go binaries because they rely on the note segment to work properly. Also, if an executable has multiple PT note segments, this algorithm is able to repeatedly infect the same binary and convert all of them into PT load segments. It's recommended to use an infection signature to avoid this. The injected host size will increase after we append the virus to the end of the file. During the analysis phase, we first locate the PT note segment while calculating the largest memory address for existing segments so we can assign a value to our newly minted PT load segment without conflicting addresses. At the end of the loop, we will cache the largest virtual memory address to this variable parasite load address. In rare cases where an executable has no PT note segment, we give up early. Then we perform a check by scanning all sections to see if this binary was compiled from Go by searching for the string Go in section names. The last block here performs a check to see if our ELF binary has been appended extra data at the end of the file. It's very rare that this would happen, and sometimes appending a virus to extra data that was already appended to the end of the file would break the binary. Therefore, we will skip them as well. The injection routine does three things in sequence, just like what we saw in the previous video. It patches the program header, section header, and then mem copies the virus. To patch the program header, it updates alignment, memory address for our virus, virus size, file offset, and adds the executable permission. These values are all calculated during the analysis phase. To patch the section header, we'll locate the entry that corresponds to our PT node segment and then overwrites the values for virus size, file offset, memory address, and added executable permission. And we're done. As simple as that. You can try out this algorithm with the following command by specifying PT note in the argument. It's able to infect 566 binaries within our user bin directory with a 97% success rate. All these failed attempts were early returns as soon as we discovered that they are compiled from Go. This is pretty neat. We have looked at 3 different algorithms now, and in the next video, let's do a quick summary and comparison before we talk about redirection techniques. Welcome back! We've introduced 3 different algorithms so far that can infect an executable with a virus you write. It'll be good to compare them since they come with different trade-offs. Before we do that, let's quickly go over how they work. The text padding infection takes advantage of the memory access control granularity. Between the executable segment and the next segment following it, there will be at most 1 page of padding that is unused, and that's where we inject the virus. The reverse text infection exploits the fact that the executable segment's start address for non-PIEs is usually fixed. The memory before this address is not used, and we reversely extend the segment to accommodate our virus. The PT node infection relies on a rarely used node segment and repurposes it into an executable segment that can be loaded and run our virus. This table sums up trade-offs between these algorithms pretty well. The PT node infection allows us to inject an arbitrary size of virus, as long as our memory fits. The text padding provides the least amount of space, but 1 page is still enough for many small viruses. The reverse text infection unfortunately only works for non-PIEs, and it will likely have the lowest infection rate, considering modern compilers by default link executables as PIE. Both PT node and reverse text infections are pretty easy to discover, even with just bare eyes. The reverse text infection has the highest complexity because we have to shift all sections to make space for our virus. This leads to more code to perform the infection. Everything is a trade-off, and there is no the best infection algorithm. It really depends on things you want to achieve. Some of you might ask, how do we come up with new infection algorithms? There are at least a couple things you need to think about. The first one is where to inject a virus to a file. Just like the text padding infection, maybe there exist other paddings in the ELF file structure that we haven't discovered yet. The readelf and obj dump tools will be your best friend to experiment and inspect file structures. Inspired by the PT node infection, perhaps there are other sections that are not needed for most programs to work. At runtime, we need to find a good place in memory for our virus. Can we create a new segment just for our virus without changing everything else? I'm sure we could come up with a brand new algorithm, but you also need to think about the complexity and effectiveness. We introduced 3 working algorithms already that need on average of 100 lines of code to infect 80% of the programs out there. But if something you design needs 10,000 lines of code to infect 30% of programs out there, it's probably not worth your time or effort. Although a good learning experience, the development and maintenance of such infection algorithm doesn't yield as much return. It's probably not something you should pursue. At this point, it's a better choice to focus on optimizing the virus code itself rather than the infection algorithm. When this video was recorded in 2024, the infector tool utilizing these algorithms was not flagged as malicious by any antivirus vendors, nor were any infected binaries. None of them recognized even the most obvious red flags, such as the presence of multiple executable segments. This concludes the chapter on virus infection techniques, and I hope you enjoyed studying these algorithms and understanding the things they exploit. You now have the skills needed to create your own unique infection method. In the next chapter, we'll discuss how to perform redirection, the final step to making a virus run as a part of an infected binary. Welcome back! We have talked about steps for compiling a virus with custom building blocks, as well as 3 different algorithms to infect an executable with a virus. In this chapter, we will complete the missing piece that is required to actually run the virus as a part of the infected binary. By the end of this chapter, you will be able to connect all the dots together and apply what you have learned. What is redirection and why do we need it? Say we have carefully engineered a virus, built it, and extracted it in a form that's ready to be injected. Then, we use one of the infection algorithms we talked about in the last chapter to find a place for this virus in the host executable. At this point, the host executable's file structure has been changed to accommodate the virus, but the virus doesn't just run as soon as it's inserted. We have yet to change the execution flow of the host. When the infected binary is run, it will not execute the injected virus. This is why we need redirection. As the last step in this workflow, we need to perform one additional modification to the infected binary to hijack the original program's control flow so we can execute the virus before the original code runs. Previously, when looking at the file structure difference before and after an infection, we only inspected the section and program header changes, but skipped some of the details on this entry point modification. In this chapter, we will talk about 2 different redirection methods and reveal how we achieve running the virus before the code from the infected binary runs. Hey, last time we discussed why the redirection step is needed. In this video, I want to talk about the most common technique used to run an injected virus first, before the host binary runs. This method is called entry point redirection. Let's review how an executable is run. The kernel first constructs all segments for the binary and assigns proper access permissions according to the program headers. Then, it will start executing the first instruction pointed to by this _start label, which is usually a part of the C runtime that gets automatically linked when the program was compiled. The startup code performs environment setup and then calls the program's main function. The entry point redirection method changes the infected binary's entry point address to point to the first instruction of our injected virus, which is the _start label that comes from the custom startup code we provided. Then, it will run the main function of our virus. When that's completed, the execution flow will jump right back to where the normal flow was interrupted. The host binary will then start running from its original entry point, which points to the original _start label. This redirect and restore pattern is what helps us achieve running the virus first and then infected binary. This is our custom startup code for viruses compiled for ARM chips. If you recall, we used a special section, text.startParasite, to hold our startup code, and our custom linker script orders it to be the first in the text section. This ensures the instruction right after the _start symbol is executed first. In order to run our virus, we will need to modify the infected binary's ELF entry point to point to this _start symbol here. This is the redirection step as we saw from the previous slide. Then, our startup code saves all registers onto the stack before calling the main function of the virus. This branch and link instruction on ARM is similar to the call instruction on x86, meaning that once we finish this subroutine, we come back to the next instruction below. After the virus is run, we restore all the registers and then run this placeholder instruction. The reason it's called a placeholder is because it's not a valid instruction. The _patch return label tells us that this 4 bytes is what needs to be patched in order to jump back to where we left off executing the original program. It's going to be a jump or branch instruction to the original entry point. This is the restoration step. From the infected program's point of view, it has no idea that the virus has run after we restore the execution flow. I have performed text padding infection on the Python interpreter again with entry point redirection. The red lines here is post-infection and green lines are pre-infection. We can see that the entry point has been mutated to point to a larger address, which was originally the padding at the end of the executable segment. After infection, this entry point lands almost at the end of the segment. The bottom is the modified section header. It just happens that our virus was merged as a part of the error handling frame section. Some of you might start to think, this seems like a particular pattern for our entry point redirection algorithm. The entry point was modified to point to a very weird address that is part of the error handling section. Normal executables by default link to C runtime startup code, and that should be part of the text section instead. Nobody's saying we should expect their program to start running inside the error handling section. I think this is a pretty big red flag that something is going on here. Similarly, I have performed PT node infection on the same binary just to show you the same pattern. If you remember, the PT node infection algorithm updates a node segment into a brand new executable segment. So together, you'll have two executable segments when you count the original one. Our entry point falls inside the new executable segment. At the bottom, it's pointing at this build ID section. Nobody should expect to start their program inside the build ID section because this section provides static information instead of code. This is just too obvious that somebody has tampered with this executable. In summary, we've learned how the entry point redirection method works and some of the undesirable side effects it can create. They could potentially be identified by antivirus software. You can experiment with this redirection method with various infection algorithms with this command above and see it yourself. Next time, I want to share with you a very stealthy redirection method that I came up with recently. Have a good one and I'll see you later. Hello! Last time, we talked about the entry point redirection that can be used to run the injected virus before the infected program runs. We kind of tricked the operating system that the first instruction in our virus is the entry point. But this method puts the entry point at a very awkward position. Depending on the infection algorithm, it's very obvious that a program's entry point shouldn't be inside of sections that do not contain code. After some elbow grease, I have devised an original method that is more stealthy. Here is the thought process. Remember, most programs are automatically linked to this CRT startup code by default, and most people are not even aware of it. In other words, almost all programs on your system could share the same piece of code. If you go to GitHub and search for glibc source, you will see that this particular piece of startup code has been fairly stable for many years. It's still being updated, but changes are related to copyright comments or other very trivial updates, perhaps 1 or 2 PRs every year. The assumption is that maybe most programs contain the same or similar blob of startup code. If we can find a way to exploit the startup code to run our virus, it would apply to almost all executables. Let's check if this assumption is true for executables in our development container. What you see above are the disassembly output of objdump for ls, pwd, and gcc. The red boxes are file offsets for the entry points. Even though the objdump didn't show the underscore start symbol here, we can deduce that these instructions following the entry point must be the startup code. When you cross-reference the source for glibc's startup code at the bottom, we can observe some similarity. I didn't show the full glibc source due to space constraint on the screen here, but you get the idea. This block of code is literally the same for all three binaries, except certain value offsets. Previously, we discovered that GCC is not a PIE, but here it has the same code as other PIE binaries. So our assumption that most programs' entry point points at very similar code is likely correct. Let's focus on one of them and observe. This first block of code sets up the stack frame and parameters for a function called libc start main. On the right, we can see the set of input parameters that are needed. This function internally calls our main function. Then we have a branch and link instruction that is similar to the call instruction on x86, which invokes this function. Since we almost always expect this block of code that calls libc start main function, why not hijack this function call to run our virus instead? In other words, we can redirect the execution flow that originally goes to libc start main to running the first instruction of our virus. After the main function of our virus finishes, we will jump back to this libc start main function and restore the flow. I call this algorithm libc start main redirection. I've performed PT node infection and this redirection on the same binary. The branch and link instruction that originally calls libc start main has been patched to branch to our virus. The implementation simply searches for the first branch and link instruction after the entry point and performs the redirection. According to the documentation from ARM, the branch and link instruction has a unique opcode that we can use. All we need to do is to match the first 6 bits to identify the instruction. In order to be more resilient to startup code changes, the implementation also searches within the first 32 instructions in case there are more instructions added in the future. If we step back a little, you'll notice that we have not changed the original entry point to some weird address. This makes it way harder to detect compared to the entry point redirection algorithm we saw last time. You can experiment with this redirection method with various infection algorithms using this command above. Even though we only went over code for ARM, the same thing unsurprisingly applies to x86 as well. The implementation of redirection algorithms can be found in the redirection folder of our virus framework. What you saw today is a typical process of designing novel algorithms. I cannot speak for all virus creators, but I always like to start by observing simple things that tend to be ignored by other people, like things we take for granted. It's very likely that you will be able to identify patterns that you can exploit. For the past 3 chapters, we studied how to build a virus, how to infect a binary with a virus, and how to run a virus as a part of the infected binary. By now, you should see how difficult it is to engineer a virus. And this is just the infrastructure that we are talking about. In the next chapter, we'll focus on the application side of things and show you how to craft your own virus step by step. Hi, this is an optional video for those who want to see how we patch instructions. It involves a bit of a math. Unless you really want to see the dirty details, you're free to skip this video. On the left, we have a branch and link instruction which gets patched into a branch instruction on the right, jumping into a different address, which is where our virus is at. It makes sense to change the destination address that we branch to, but you might wonder, why do we change the instruction type from branch and link to branch? The difference between these two instructions is that the former will save the return address to a register, so when the subroutine is finished, the program flow can come back to the next instruction below. The branch instruction simply jumps to another location without saving the return address. The next instruction below the original branch and link instruction is calling the abort function. Basically, the author of this startup code never expects we return from libc start main function, which is what the comment below states. Our virus framework could patch the new instruction to be branch and link, but I think a branch is more appropriate here since this is what it does with less side effects. The ARM assembly instructions have a concept of opcode, which is similar to instructions for other chips such as x86. The red boxes highlight what the opcode looks like. It's basically a part of the instruction. In this case, the first 6 bits that the CPU can use to identify what type of instruction it is. If the first 6 bits are 100, 101, it's a branch and link instruction. If it's 000, 101, it's a branch instruction. And of course, there are different opcodes for different instructions. The last 26 bits encode the destination offset divided by 4. For example, if the value of the offset is 0x04, and we're jumping to an address that is 4 bytes away from where this branch instruction currently is, the value for the last 26 bits would be 4 divided by 4, which is 1. Going back to the branch and link instruction on the left, our job is to figure out where the original address we want to jump to, save it, change the instruction to jump to the address of our virus, and then update the virus to jump back to where it should go originally. Let's see an example how we can do this calculation. The original branch and link instruction is encoded as 0x97FFF880. When you rewrite it in binary form, the first 6 bits are 100101, which matches the opcode of the branch and link instruction. If you mask out the opcode, you get the value for the last 26 bits. And when it's multiplied by 4, plus the current instruction location, you get the original address it jumps to, which is where the libc start main function is. We have injected the virus into the file, and we know the address where the virus is loaded. Suppose the first instruction of our virus is at 0x40000. The new offset can be calculated by subtracting the current location from it, and then divide by 4 to get the value for the lower 26 bits. After adding the opcode for a branch instruction, we have assembled the final instruction, and it is what you see on the right. This whole process is a bit tedious if you work it out by hand, but it's a piece of cake when you do it in code. You can find the implementation of the address calculation inside the redirection folder of our virus framework. The instruction encoding for x86 is a bit messier, but the principle is the same. I know math sucks and nobody wants to do it. For those who have watched this video, I hope it will come in handy when you need it. Hello! This video starts a new chapter on virus engineering. We will be talking about how virus propagates first, and then walk through some example code to show you what a virus can do. At the end, we will guide you through all the steps how a virus is created, for research purposes of course. It's going to be a fun chapter, and let's begin with the first topic, propagation. During the demo at the beginning of this course, we built a sample virus and used an infector tool from the virus framework to infect a binary. This process of infecting a patient 0, which later organically infects other binaries, is called bootstrapping. The patient 0 is then deployed to a target machine, for example via social engineering. Whenever you see a website that's offering a free cracked version of the software, which would otherwise cost hundreds of dollars, you should probably think twice. Viruses take advantage of human nature to spread, because who doesn't want to save a few $100? Once the program you downloaded is executed on your machine, the attached virus will also run, searching for more programs to infect in order to maximize survivability. Some particularly smart viruses can also spread to other machines on the same network, just like the Morris worm we talked about early in the course. How is propagation done? We will talk about that in depth in the next couple videos. Hello and welcome back. Let's talk about propagation. Just like diseases, computer viruses can also spread from one part of the computer to another. And this is what makes it so nasty when you attempt to recover from an infection. You would literally need to scan all files on your system and disinfect them one by one. Some antivirus software has a quarantine feature that puts infected files inside a sandbox to prevent further spread. Remember, when an infected program is run, we executed the virus first, before the original program. This could be a problem if the virus runs too slowly. Performing a large directory tree walk could take a long time and become noticeable to users. People might wonder why a program that usually finishes within a blink now takes a couple seconds. Here is the trade-off. The more files we search and infect, the less likely a virus can survive, as it tends to catch attention. People use a technique to execute virus code in a forked process that can run in parallel to the original host program. This solves the slowness problem, but can be equally noticeable if there's a new process popping up when users look at current running processes via tools like top. There's no best approach here, but I'd vote for running in a forked process and hide it behind a name that sounds innocent, such as kernel task you see above. You can also perform a random infection up to a maximal number of attempts in a forked process, so the spawn process is very short-lived, and hopefully it disappears before anyone sees it. The virus framework has some libraries you can use. The double fork helper can execute arbitrary work wrapped in a lambda or callable inside a fork process. This one you see here is more sophisticated than simply forking a child process because it could create zombie processes that are very noticeable. Zombie processes are created when the parent of a child process terminates before the child terminates, leaving it in a state that needs to be cleaned up. The double fork technique avoids this by forking a child first, which then forks a grandchild to perform long-running work. The parent process performs wait and cleans up the child process when it dies. The grandchild, after finishing work, has no parent anymore, which will then be cleaned up by the init process. This is a pretty cool trick to avoid zombie processes and is particularly suitable to use by a virus to hide its tracks. We also have iterators you can use to walk through all files within a directory, even recursively in subdirectories with a simple for loop. Everything is implemented using the libraries that are virus-friendly. In other words, they do not link to any external libraries or contain global variables. We can find these helpers in the common folder of our virus repo and check the associated unit tests to see how to use them properly. In the next video, we'll walk through some code to show you how these functions are used. Welcome back! Previously, we introduced helper functions that can be used to perform virus propagation. In this video, let's walk through the code to see how to put everything together. It's too long to fit on a single slide, so let's look at different parts of it. This function is called propagate. It takes no input argument and returns the number of successful infection attempts. It requires 3 template arguments. The first one is the directory iterator type, which can be a normal or a recursive iterator if you want to search child directories. The second template type is the infector. You can use the algorithms we learned in the previous chapter, such as text padding or ptnote infectors. The last template type is a redirector. You may use entry point or libc main redirector that we introduced previously. This interface shows the modular nature of our virus framework. You can easily devise new building blocks and plug right in. If you forget how infection or redirection work, feel free to revisit these two chapters. The propagate function must be invoked inside a virus because these two functions, get parasite start address and get parasite length, require the symbols we exposed inside our custom linker script. The parasite start symbol tells us the address where virus code starts, and the parasite end symbol tells us where the virus code ends. If we subtract them, we get the total size of the virus. This information will be used to create a span that represents the block of bytes for our virus, which will later be replicated. Then, we create a string on the stack with a single dot inside. The dot means we will start searching for other binaries to infect from the current directory. It's a bit awkward because usually you can just use a string. Remember, we want to avoid depending on RO data, and that's why a small array on the stack is used. Now, we're ready to iterate through all the files. The first thing we do inside the loop is to open each file. If for some reason we lack permission to open and read, we'll simply skip it. The second block of the code maps a file into memory and uses a span to represent a block of bytes for the file that will be later used by infection algorithm. Then, we construct a string by appending a dot to the end of the original name. We'll use this name to create a brand new file that will be a scratchpad for infection. The infection is performed by calling the infect function, which returns a new file descriptor. If the returned file descriptor is valid, it means the infection is successful. After a successful infection, we'll perform an atomic swap between the copy of the program that is infected and the original program. It's possible we lack permission to do so. In that case, we'll give up and remove the temporary file we created. And that's the whole propagation process. Last time we talked about trade-offs of performing large directory tree walk. The propagation process can take a long time, but the double fork function can be used to execute code concurrently with the infected host. In summary, we looked at the propagation function and showed how it works internally. The flow is very simple. We open the virus and map into memory, iterate through each file, and create a copy of the file to be infected. If successful, it will replace the original. For those who are interested, you can read the source code inside the propagation folder from our virus repo, and I'll catch you next time. Hello and welcome! Last time, we talked about a virus propagation flow and how the propagate function works. Let's see some example viruses that make use of it. We have looked at the self-propagating virus before because this is what was used in the demo at the beginning of the course. We first include some headers where we get all the building blocks that will be passed to the propagate function. In this case, we're using a recursive directory iterator with a max search level of 2. Then, we specify the virus should perform a PT node infection and use the entry point redirection to run the virus. The entire replication process will happen inside a forked process, so when users run the infected program, it should not be noticeable. Everything is encapsulated inside the forked propagate function. With a single function call, your virus is now highly infectious, and all it does is to print hello world. For those who are not familiar with the Bazel build system, in order to compile the virus, we will need to specify a target in the build file. We have one build file per directory, and each buildable target inside the directory would need to be specified in the corresponding build file. The cc no-std-lib binary macro is our custom rule for building a virus. CC means we're building a C or C++ program, and the no stdlib means we will not link the standard glibc or startup files. Instead, we'll use a custom linker script, our own version of the libc and a startup code for reasons we covered in the previous chapter, how to build a virus. The name parameter must be unique within the entire repository, and that's what will be used when we run the compilation command. We want to build a self-propagating virus inside the virus directory. The directory is also called a package in Bazel terminology. The Bazel build command takes an argument starting with double slashes, the package path, and then the target name. The sources parameter captures a list of source files that need to be compiled. The allow RO data merging is a feature that allows us to combine the text section with RO data section and inject them as a single binary blob for viruses that absolutely need to use RO data. In general, you should try to avoid RO data because it can break infection for some algorithms. The depth argument is a list that specifies other targets our virus depends on. We use directory iterators, infection and redirection algorithms, and they must be specified here. After this block is added to the build file, we can run the Bazel build command to compile the virus. Here is another example virus. It's called self-propagate libc start main. Similar to the previous one, it randomly prints a quote depending on the virus memory address, and then performs propagation to other programs using the libc main redirection method we talked about. If you get infected by this virus, every time you run a program, you will see a random quote on the screen. Once you have compiled a virus, you would want to perform bootstrapping by dropping the virus onto a binary first before it can spread. We have an infector tool that does exactly this. All you need to do is to compile it and provide the compiled virus and algorithms to perform the infection. The infection algorithms used here is independent from what our self-propagating virus uses internally. The infector tool will infect a copy of the specified binary in the temp folder and name it as victim. Whenever you run the infected copy, it will try to spread virus in the current directory, so be very careful. I hope you can see the pattern of creating a self-propagating virus, and I encourage you to experiment with the code on your own. If you have messed up the development container, you can create a new one and start over. No big deal. In the next couple videos, I'll talk about some other things you can do inside a virus, like sending data over the network, a reverse shell, and finally, introduce a way to create a fileless virus that doesn't need to live on your file system at all. Have a good one, and I will see you next time. Hello there! Starting from this video, we'll shift the focus from virus propagation mechanisms to virus application code, and look at things you can do inside a virus. A virus is just like normal software you write, although with a bit of limitation. Viruses don't usually perform heavy work, because attackers don't want to catch too much attention. Also, remember what we talked about in the past. The virus code must be position independent, self-contained, and not linked to any external libraries. Let's start with a simple virus that collects data from an infected machine and sends back to a server that is owned by the attacker. Imagine in a hypothetical situation, our friend Bob downloaded an infected program and ran on his machine. The virus was executed when he ran the program. What the virus could do is to gather user information or anything that invades his privacy and then sends to remote server via network sockets. If the infected program is downloaded by multiple people around the world, the attacker can aggregate serious amount of information. To push this even further, The attacker can make this communication bidirectional, allowing them to issue commands to perform various tasks, such as distributed denial of service attacks. Our poor man Bob, among others, have contributed to attackers' botnet, which is a network of machines that are being controlled to do whatever the attacker wants. With a large number of machines under control, you might have heard of botnet for hire service. Anyone can pay some bitcoins to rent random machines to perform all kinds of evil. I want to show you a very simple example how a virus can send data over the network. The virus framework provides various system call wrappers that enable you to do standard socket programming. The code snippet you see above opens a UDP socket and configures the IP address of an imaginary attacker's server. We're using a hard-coded IP here, but realistically, it could be a static address for machines that attackers rent from various cloud providers that are reachable from all over the world. Then, the virus sends some data to the specified address before exiting. In this case, it sends a string, but it could be more sophisticated. We can pretend to be the attacker by running the netcat tool, waiting for incoming UDP datagrams. Let's see it in action. We will first connect to our development container. And then let's build example virus. In case you haven't built the infector tool, you can use this command to do so. And now let's infect the pwd program. The infected program is saved in the temp directory and named as victim. Let's open another terminal. In this terminal, we'll pretend to be the attacker's machine and run the nc command listening for incoming UDP datagrams. And now, let's run the infected program. As you can see, the attacker is receiving data every time the infected program is run. This virus might sound simple, but it's a good baseline you can build upon. In the next video, we'll see a more advanced version of this virus, where the attacker spawns a reverse shell. Hello! In this video, we'll talk about an example virus that gives an attacker complete control over an infected machine. Remember what we did in the last video. In order to establish network connections, you first need to know the IP address of the host, and then initiate the connection. Imagine you have a corporate network that is protected by a firewall on the left. It's extremely hard for an outside attacker to initiate connections to these machines, because they could be using non-public IPs. In addition, any outside connections will likely be screened by a firewall with very strict rules. If you have an internet-connected server and look at connection logs, you'll be surprised by how many random attempts are made from people trying to get inside your machine. There are tools that can scan random machines and just keep trying weak passwords to see if they can log in. There is something called a reverse shell that are used by attackers to circumvent various protections. Instead of having an attacker initiate a connection from outside, a reverse shell is started from the inside, and the attacker takes on a passive role of waiting there and accepting connections. Because the connection is initiated by an inside machine, it's extremely hard to be blocked by a firewall, as it cannot reasonably tell if the connection is intentional or not. In reality, you would need sophisticated system monitoring for suspicious command execution and track all outgoing connections to detect a reverse shell. It's very difficult in practice to get things right without false positives. So the whole idea is, if a victim machine runs an infected program and executes a reverse shell virus, we will be able to gain control of that machine. Let's see some code. In the virus directory, there is an example reverse shell virus. We first create a lambda function that wraps all the work that will be performed, and it is passed to the double fork utility to execute work concurrently in another process. Because eventually we need to spawn a shell, it's best to do inside a new process without affecting the original program. The first part of the work we perform is to set up the address of the attacker's machine. It's essentially the server we're trying to connect to. I'm using a hard-coded address here, but in practice, it should be a static IP that is accessible publicly. Then, we create the socket and try to connect to the attacker's machine. It uses a retry loop here just in case the connection fails. Now, this block of code is very important. We invoke the dupe syscall to update stdin, stdout, and stderr file descriptors to refer to our socket. Stdout is the output stream when programs print to a terminal. For example, this is where we usually print hello world to. stderr is similar, but by convention used for printing errors. stdin, on the other hand, is providing input to the terminal. Simply speaking, we redirect all the input and output streams to our TCP socket, so when we execute the shell, the attacker can see the output and provide input over the network. The socket is what's bridging the attacker to the newly spawned shell on an infected machine. Let's see this virus in action. We will first build the virus. And also, let's build the infector tool. Then, let's infect the pwd program. In another terminal, let's run netcat and listen for incoming TCP connections. I want to make it feel more realistic by opening a terminal on my Mac outside of our development container to simulate remote connections from a different machine. Before we do anything, let's run ps to show the currently running processes on the infected machine. Right now, we have the zshell process as well as the ps command I just ran. Now, let's execute the infected program. And the terminal on my Mac has access to a shell for the Linux development container. It looks a bit weird because it's raw I/O over a socket. We can follow these steps to promote the shell to a fully functioning bash with command history and colors. First, let's upgrade our shell to bash. And this is how we get our prompt back. Then, let's background the current shell. We also need to update the local terminal line settings. And then, let's get our color back. Let's head back to the victim machine and see the current running processes. And indeed, we have one more shell process that is being used by the attacker. Pretty cool. This shell works just like what you would get when you connect to a machine via normal means like SSH. We can even spawn a Z shell on top of this. You get full command history and a fully functioning Vim editor. You can poke around just like your own machine. As you can see, as soon as the infected program is run, a reverse shell was spawned and gave an attacker basically complete control, just like a normal user. If the same reverse shell virus infects a large amount of machines, the attacker can potentially build an automated service waiting for infected machines to connect, and then drop more viruses on them. I hope you are having fun and get a chance to test this virus. In the next video, I will show you how a fileless virus works. Hello and welcome back. I want to talk about a technique the virus writers use to make their code more stealthy. Normally, a virus lives inside an executable stored on disk. Antivirus software may periodically scan your hard drive to locate threats. There is a way to circumvent protections and run malicious code without touching the file system by downloading it from the internet and then perform memory-only execution. Because the downloaded code lives in memory, antivirus software in general would have trouble monitoring it. Memory update speed is way beyond disk update speed, so monitoring memory changes without destroying system performance is very hard. If antivirus softwares slow down people's machines, they will likely go out of business. In addition, memory-only execution makes incident investigation harder. As soon as an infected machine's power is turned off, the malicious code in memory is gone. People can no longer perform static file analysis when there is no file. The fileless virus relies on a system called memfd_create. Just like normal file descriptors, when you open a file, you get a descriptor that only has volatile backing storage using memory. It can perform most of the operations just like a normal file, except there is no file. The idea is we infect a program with a small piece of code that downloads malicious payload into memory-only file created from the memfd syscall. Then we execute it as if it were a real executable file on disk. Of course, the attacker needs to spin up a server that provides the malicious code remotely. Every time an infected program is run, it will fetch more code in the background and silently execute it from memory, all without leaving a trace on the file system. We have an example fileless virus in the repo. Similar to examples we saw earlier, we wrap all the work inside a lambda and then run it in a forked process concurrently without affecting the original program. We first create an anonymous file descriptor using the MFD and then truncate it to a predefined size. In this example, it's using 1 megabyte, which could be bigger. Then, we run the download function to fetch additional code from a server via TCP. Again, I'm using a hard-coded IP address here for demonstration purposes. After a successful download, the malicious code is run using the exact syscall. This is a very interesting technique because it allows the attacker to serve arbitrary code remotely. The malicious code can be improved iteratively and then sent over to infected machines like an over-the-air update. Let's see this in action. We first compile all the code in the virus folder as well as the infector tool. For this demonstration, we'll need the fileless virus as well as the fileless virus server that provides the malicious code remotely. The 3 dots here means we're building everything inside the virus directory. Let's infect the good old pwd program. Then, let's spin up the server in another terminal and specify a file that our infected program will be downloading. The compiled server program lives in the temp directory, and the first argument is the malicious file it was sent to infected machines. Let's use the victim PIE binary that just prints some text and then sleeps forever. Going back to the infected machine, Let's see what is running with PS. Now, run the infected program. It prints out the current working directory as well as this extra text that comes from the downloaded code. Let's run PS again. There's a process that has a file descriptor number as the name. This is what was started by the fileless virus. It also has a PID. So let's inspect its memory address, just like what we did in the first chapter. The rightmost column didn't give us the file name where these segments came from. It's showing memfd deleted because there's no file to be found on disk. Let's kill this process that runs malicious code from memfd. And then let's tell the server to provide a different payload to serve. I have a copy of the reverse shell written in bash. Let's use that and see what happens. In another terminal, let's open netcat and wait for TCP connections. Now, let's run the infected program. The fileless virus has downloaded a reverse shell code this time. As soon as the infected program is run, the attacker has access to a shell, just like what we saw in the previous video. This is it. Our fileless virus successfully downloaded 2 different pieces of code and ran them without touching file system at all. Because of the nature of downloading payload, the attacker can drop things dynamically onto victim machines. The virus can even remain dormant if the attacker decides to shut down the server and turn it back on a future date. This is a powerful evasion technique that's getting more publicity in the recent years. I strongly recommend you to follow along this video and run it yourself. Have fun, and I will see you next time. Hello and welcome back. For this entire course, we talk about things people exploit, either holes in software or weakness in human nature. Sometimes, virus writers leverage software engineering trade-offs or even optimizations to spread viruses. So what can we learn from this? The first thing is, there is no perfect system or software. In software engineering, you typically have short and long-term goals, and of course, a whole bunch of tech that nobody knows when they will be fixed. For some companies, software change all the time to cater to shifting requirements. It's common when engineers quit their jobs and you end up with nobody understanding the code. Who's going to maintain it? Under pressure from your CEO, you would hire new engineers who tend to completely redesign the software. Then, they quit the job too. You're back in this endless cycle with a piece of software nobody knows how to fix. A word of advice: do not assume things is secure and let your guards down just because it comes from a big name company listed on NASDAQ. Don't be surprised if someday the software they provide is exploited in the wild, or it simply crashes computers globally. The second advice is, do not trust anyone on the internet. If you found a cracked version of software that would otherwise cost hundreds of dollars, stay away. If your friends send you some executables to run on your computer, you probably need to reconsider this friendship. Do I need to mention that you have watched the entire 4-hour course made by a random dude on the internet? Don't worry, your computer is safe because hopefully you have set up the development container. It's very unlikely anyone is able to access things outside. Use your judgment before downloading anything, and especially those that require root passwords. Social engineering is out of scope of this course, but I just want to mention this term in case you want to read up on it. In one word, don't get tricked to run software you don't know from the internet. It's the most effective way for virus to spread. For this course, we didn't talk about privilege escalation. Basically, the viruses we focused on have the same permission as the infected processes. If you run it as a normal user, it will not be able to infect anything inside user bin. But some hackers have figured out ways to go from an user account to a super user account with full privileges. Then your virus will become a lot more lethal. So remember to update your system and software regularly to pick up the latest patches. Like I stated in the beginning of the course, it's not trying to teach people how to write viruses, but rather reveal how they could be made. Just to quote VX Heaven, which is one of the famous forums for people to discuss malware, viruses don't do harm, ignorance does. If we do not know our enemies, how can we defend ourselves? I hope you can walk away with useful knowledge and a different perspective, whether it's how you design your software or systems. Share the knowledge with your colleagues and friends. It's also a fun topic during parties too. Ethical hackers are a group of people who operate within the boundary of laws. They do not access information illegally, and they typically need a company's permission before hacking. Any findings must be kept confidential so companies can get a chance to fix the bugs. They hack just to demonstrate what real cyber criminals might do. For those who are excited to push the frontier of virus engineering and start cooking whatever is hiding in your back pocket, you're responsible for your own actions. Remember the Morris worm? The author got his punishment, even though it's just an experiment. There are many nice things outside of jail, so don't cross the line. Where do we go from here? I have linked a repo full of Linux malware source code, either leaked or decompiled for research purposes. I suggest you take a look and appreciate the fact that we're just scratching the surface in this course. There is much more out there, with new techniques being discovered. The knowledge you learned should be sufficient to help you implement novel algorithms and study their effectiveness. Carry on the momentum. I started the virus framework merely as an experiment. You never know what your experiment can turn into. If you have found something interesting, please submit a PR to the virus repo. I would love to learn from you. Also, I'd appreciate if you leave comments, feedbacks, and let me know how this course can be improved. All right, that wraps up this entire course. Congratulations and happy hacking. Hello, this is the last chapter of this course. I want to provide a quick summary of the contents and talk about where to go from here. We introduced the Linux ELF format that tells the kernel how to load executables into memory and run them. There are lots of details about the format, but the most important pieces are the ELF, section, and program headers. Each of them captures different levels of information. We also look at executable loading process and put everything together, from bytes on disk to segments in memory. Then we discuss what happens at a program's entry point and introduce the C runtime startup code, which I bet is something most people are not aware of. This chapter on ELF format might be a bit boring, but it sets up the foundation for virus building and infection algorithms. If you ever want to figure out a new way to exploit the ELF format, you have to understand the standards and potentially read the kernel source. Building a virus is similar to building normal software. We discussed various challenges and workarounds. In order to make a virus survive in most programs, it must be built as position-independent code to facilitate relocation. Dynamically linking to libraries are not allowed because a virus doesn't have the luxury to use the dynamic linker to load and resolve external symbols. Therefore, it must be statically linked. We need to avoid running C runtime twice, and that requires our own startup routine. The custom linker script is also used to organize sections of our virus in a way that is extraction friendly, so we know exactly where the first instruction of a virus is. Our virus framework takes care of all these things automatically for you, but you can see it's quite involved to even write a simple Hello World virus. Once a virus is built, the text section will be extracted and it's ready to be injected into other executables. We introduced 3 different algorithms to perform infections, and they all have distinct trade-offs. There is no best algorithms, and it really depends on how you balance stealthiness, effectiveness, and complexity. Perhaps a good algorithm is the one that you actually can implement and understand. After you infect a program with a virus, the last step is to mutate ELF structures to actually run it. A common way to do this is to redirect the entry point to point to the start of our virus so it runs before the infected program. We also introduced a way to redirect the libc main start function to run our virus. I really like this method because it doesn't move the entry point to weird sections that shouldn't contain executable code, but it's a bit more complex. We then pivoted to virus engineering and talked about how they propagate. Essentially, a virus needs the ability to know the start and the end address of itself, and then memcopy to another executable. There are several trade-offs in the replication process, namely speed and stealthiness. You can infect a lot of files sequentially, but it would cause noticeable slowdown. If you fork a new process to do it, it could be suspicious to system administrators. But none of the commercially available antivirus software engines thinks the self-propagating code we wrote is malicious. If you do that on Windows, it would likely be quarantined immediately as soon as you finish compiling the virus. Then, we studied interesting viruses even when they are not contagious. The reverse shell virus can circumvent firewalls, and the memoryless virus can be controlled remotely without leaving any trace on disk. There are a lot you can do inside a virus, but you get the idea. In the next video, I want to give you some advice and talk about things we learned when researching viruses.